Hello, and welcome. It's good that you're here, wherever you are, whatever time has brought you to this moment of stillness. Tonight, we're going to explore something that hums beneath your feet even now. Something vast and patient and warm. A force that has shaped every mountain you've ever seen and every island that rises from the sea. We're going to talk about volcanoes and the deep, slow energy that lives inside our planet. You can let your shoulders settle if they haven't already. There's no hurry in what we're about to discover together. Perhaps you've had a long day, or perhaps you're simply ready to let your thoughts drift towards something larger than the small concerns that filled your hours. Either way, you're welcome here. The science we'll explore tonight asks nothing of you except your curiosity, and even that can be gentle. If these journeys bring you comfort, you're welcome to return anytime. There will always be more to discover, more quiet facts waiting in the dark. So let's begin, slowly, with something you might not have considered before. The ground beneath you, right now, is warm, not just from the sun that touched it during the day, but from something far deeper, something that has been burning since before there were eyes to see it burn. The earth generates heat. It makes its own warmth, continuously, reliably, like a heart that never stops beating. This isn't a metaphor. Deep inside our planet, in places no human has ever been and likely never will be, temperatures rise to levels that would vaporize anything we might send down to measure them. And yet this heat doesn't simply sit there, static and contained. It moves, it flows, it rises through rock and metal and time itself, carrying energy from the core toward the surface, toward the thin skin of the world where we live our lives. This movement is slow beyond human comprehension. A plume of hot rock rising through the mantle might take millions of years to complete its journey, but it never stops. The earth is always in motion, always shifting, always redistributing the warmth that was born in its depths. And sometimes, that warmth finds a way to reach the surface. When it does, we call a volcano. But before we talk about volcanoes themselves, let's stay for a moment with this idea of Earth's inner energy, because it's one of the most quietly magnificent things about our planet. The heat inside the Earth comes from two main sources, and both of them connect us to the very beginning of everything. The first source is ancient. When the Earth formed, about 4.5 billion years ago, it came together from countless smaller pieces, fragments of rock and metal that collided and merged in the early solar system. Every collision released energy. Every impact generated heat. And as the planet grew larger, that heat became trapped inside, insulated by layers of rock that formed around it. Some of that original heat, that primordial warmth from the birth of the world, is still down there. It hasn't escaped. It's still radiating outward, still warming the deep interior, still contributing to the slow convection currents that move through the mantle. The second source is even more remarkable. Deep in the Earth's core and mantle, radioactive elements are quietly decaying. Uranium, thorium, potassium, and other unstable atoms are breaking apart, transforming into different elements, and in the process, releasing energy. This has been happening for billions of years. It will continue for billions more. The Earth is, in a very real sense, powered by a nuclear reaction, a slow and steady release of energy that has no off switch, no pause button. It simply continues, patient and inexorable. These two sources, the ancient heat of formation and the ongoing warmth of radioactive decay, combine to keep the interior of our planet hot. And that heat has to go somewhere. Most of it escapes slowly, seeping through the crust in ways we barely notice. The ground radiates warmth into the air and water above it, releasing energy at a rate too gradual to feel. But in certain places, the heat finds faster pathways. It concentrates, it gathers, and it rises with enough force to melt rock. When rock melts deep underground, We call it magma. And magma, being less dense than the solid rock around it, wants to rise. It's buoyant, like oil in water, and it pushes upward through cracks and weaknesses in the Earth's crust, seeking the surface. Most of the time, magma never makes it all the way up. It cools and solidifies underground, forming vast chambers of once molten rock that will never see daylight. But sometimes, the magma finds a path. It reaches the surface, and when it does, when that liquid rock emerges into the open air, we call it lava. Lava is one of the few ways we can directly observe the Earth's interior. It's a window into conditions that exist miles below our feet, a sample of the deep planet brought up into the light. And despite its reputation, despite the dramatic footage of glowing rivers and explosive eruptions, lava is, in many ways, remarkably calm. Consider the speed at which lava typically moves. In most eruptions, lava flows advance at a pace you could easily outwalk. Some flows move only a few meters per hour. They creep across the landscape like slow, glowing syrup, giving plants and animals and people plenty of time to move out of the way. There are types of lava that flow faster, of course, particularly when they're very hot and very fluid, but even these rarely move faster than a running person. Lava is patient. It doesn't chase. It simply advances, steady and inevitable, following the contours of the land, filling low places, cooling at the edges while the interior remains molten. And as it cools, lava does something wonderful. It becomes new land. Every volcanic island in the ocean, every volcanic mountain on a continent, is made of layer upon layer of cooled lava, stacked over thousands or millions of years. The ground that seemed so permanent, so ancient, was once liquid. It flowed, it glowed, and then it stilled and became the foundation for everything that would grow on it afterward. Hawaii, Iceland, the Galapagos Islands, all of these places are volcanic constructions, built slowly by repeated eruptions, each one adding a new layer to the structure. The islands didn't rise from the sea in a single dramatic event. They grew, incrementally, over immense spans of time, as magma pushed up from below and solidified into rock. This process is still happening. Right now, as you rest, there are volcanoes adding new rock to the Earth's surface. The island of Hawaii is still growing. On its southeastern flank, a volcano named Kilauea has been erupting on and off for decades, sending lava flows down toward the ocean, where the molten rock meets the water and hardens into new coastline. The island is expanding, slowly, quietly, in a process that has been ongoing for hundreds of thousands of years. And beneath the ocean, even more volcanic activity is taking place, hidden from view. The longest mountain range on Earth isn't the Himalayas or the Andes. It's the mid-ocean ridge system, a chain of underwater volcanic mountains that stretches for more than 40,000 miles, wrapping around the planet like the seam on a baseball. Along this ridge, magma rises continuously from a mantle, creating new oceanic crust, pushing the seafloor apart in a process called seafloor spreading. This is how the Atlantic Ocean grows wider every year. The Mid-Atlantic Ridge, running down the center of the ocean, is constantly producing new rock, and as that rock forms, it pushes the continents on either side a little farther apart. The rate is slow, only a few centimeters per year, about as fast as your fingernails grow. But over millions of years, those centimeters add up. They become thousands of miles. They reshape the map of the world. And this brings us to one of the most calming realizations about volcanoes and Earth's inner energy. Everything is connected. The heat in the core drives convection in the mantle. Convection in the mantle moves tectonic plates. Moving plates create volcanoes. Volcanoes build land. Land erodes and returns to the mantle. And the cycle continues endlessly, on timescales so vast that human civilizations rise and fall in what amounts to a single heartbeat of the planet. You are living on a world that is constantly renewing itself. The mountains that seem eternal are temporary. The oceans that seem unchanging are shifting. And the ground beneath you is part of a system so large and so patient that it makes our longest histories seem like moments. Let's think about the structure of the Earth for a moment, because understanding how our planet is layered helps make sense of where all this energy comes from and how it moves. At the very center of the Earth is the inner core, a solid sphere of iron and nickel about 1,500 miles across. Despite being at the center of the planet, where pressures are immense, the inner core is solid because the pressure is so great that the metal cannot melt, even though temperatures there reach about 9,000 degrees Fahrenheit. That's roughly as hot as the surface of the sun. So deep inside our planet, in a place of absolute darkness, there's a heat that rivals the light of our star. Surrounding the inner core is the outer core, a layer of liquid iron and nickel about 1,400 miles thick. This liquid metal flows and swirls, driven by heat and the Earth's rotation, and these movements generate the planet's magnetic field. The magnetic field is what protects us from harmful solar radiation, what makes compasses point north, what creates the shimmering auroras near the poles. All of that, the invisible shield that makes life on the surface possible, comes from the movement of liquid metal deep underground, driven by the Earth's inner heat. Above the core is the mantle, a thick layer of hot rock that extends from about 1,800 miles below the surface all the way up to within a few miles of where we live. The mantle makes up about 84% of the Earth's volume. It's not liquid, exactly, but it's not quite solid either, not in the way we usually think of solid things. Over long periods of time, the rock in a mantle flows, deforming and moving like an incredibly thick fluid. This is the layer where convection happens, where hot rock rises and cool rock sinks, creating the currents that drive plate tectonics and volcanic activity. And finally, at the top, there's the crust, the thin outer shell of the planet where we live. The crust is only about 3 to 30 miles thick, depending on whether you're under an ocean or a continent. If the Earth were an apple, the crust would be thinner than the skin. And yet this thin layer is where all of geology happens, where mountains rise and valleys form, where earthquakes shake and volcanoes erupt. The boundary between the crust and the mantle is called the Mohorovičić discontinuity, or the MOHO for short, named after the Croatian scientist who discovered it. It's not a sharp line, exactly, but a transition zone where the properties of rock change, where the cooler, more rigid crust gives way to the hotter, more flexible mantle below. And it's at this boundary, and in the upper parts of the mantle, that most magma forms. When conditions are right, when the temperature is high enough or the pressure drops enough, the rock begins to melt. Not all at once, and not completely. Rock doesn't melt the way ice melts, transitioning cleanly from solid to liquid. Instead, it melts partially, with some minerals liquefying while others remain solid. The liquid portion, being less dense, separates from the solid and begins to rise. And as it rises, it can gather into larger pools, forming magma chambers that sit beneath the surface, waiting. Some magma chambers are enormous. The one beneath Yellowstone National Park, for instance, is estimated to be about 37 miles long, 18 miles wide, and several miles deep. It contains enough molten and partially molten rock to fill the Grand Canyon more than 11 times over. And yet, despite its size, despite the immense heat it contains, this magma chamber sits quietly beneath one of America's most visited parks, warming the ground, heating the water that feeds the geysers and hot springs, but not erupting. It has erupted in the past, catastrophically, but not in more than 70,000 years. And it may not erupt again for tens of thousands of years more or longer. The magma is patient. It has nowhere else to be. This is one of the most important things to understand about volcanoes. Most of the time, are not erupting. They're resting. The magma beneath them is there, yes, but it's contained, stable, cooling slowly or being replenished slowly, existing in a state of balance. Eruptions are the exception, not the rule. They happen when something changes, when new magma pushes in from below, or when gases build up enough pressure to fracture the rock above, or when the chamber shifts in some way that opens a path to the surface. And even when eruptions do happen, they're often gentle. The explosive, catastrophic eruptions that make headlines are rare. Most volcanic eruptions are effusive, meaning they produce lava flows rather than explosions. The lava emerges relatively calmly, oozes out onto the surface, and spreads. There's no blast, no towering ash cloud, just liquid rock finding its way into the open air and cooling in a new land. Hawaii's volcanoes are classic examples of this. Kilauea and Mauna Loa erupt frequently, but their eruptions are usually non-explosive. Lava flows from vents and fissures, sometimes fontaining into the air in glowing arcs, but more often simply welling up and flowing downhill. People can, and do, approach these eruptions safely, standing close enough to feel the heat, to hear the hiss and crackle of cooling rock, to watch the surface of the flow wrinkle and fold as it moves. There's something almost meditative about watching lava flow. The movement is constant but slow. The colors shift as the surface cools from bright yellow-orange to deep red to black, while cracks in the cooling crust reveal the still molten interior glowing beneath. It's mesmerizing in the way a campfire is mesmerizing, a play of light and heat and transformation that draws the eye and quiets the mind. And the heat itself, the radiant warmth of molten rock, is a tangible connection to the Earth's interior. When you stand near a lava flow, you're feeling heat that originated miles underground, heat that has traveled through solid rock, heat that represents the slow release of energy that has been stored in the planet for billions of years. It's a physical link to deep time, to processes that dwarf human experience. Volcanoes also create some of the most fertile soil on Earth. When lava weathers and breaks down, it releases minerals that plants need, nutrients that were locked in the rock. Volcanic ash, too, is rich in minerals. After an eruption, once the immediate destruction has passed, the land often becomes extraordinarily productive. Some of the most lush, green, densely vegetated places on Earth are volcanic. The slopes of volcanoes in Indonesia, Central America, and East Africa support thriving forests and farms. The soil is dark and rich, and things grow with remarkable vigor. This is part of the cycle, part of the way the Earth renews itself. Volcanoes take rock from the deep interior and bring it to the surface. Weathering breaks that rock down into soil. Plants grow in the soil. Animals eat the plants. And when the plants and animals die, their remains mix with the soil, adding organic matter, creating a living layer on top of the volcanic rock. Over time, ecosystems develop, complex and resilient, all built on a foundation of cooled lava. And then, eventually, the volcano may erupt again, covering the ecosystem with new rock, resetting the process. But even this is not an ending. It's a transformation. The buried organic matter becomes part of the rock record, a thin layer of carbon and nutrients sandwiched between layers of basalt, preserved for millions of years. And on the new surface, life begins again. This cycle has been happening for as long as there has been life on Earth. Volcanoes have been erupting for billions of years, long before there were plants or animals, long before there was oxygen in the atmosphere. In fact, volcanoes played a crucial role in creating the atmosphere we breathe. Early in Earth's history, the atmosphere was very different from today's. It contained little to no oxygen, and much of the water vapor, carbon dioxide, and other gases that made up the early atmosphere came from volcanic outgassing. Every time a volcano erupts, it releases gases that were dissolved in the magma. Water vapor is the most abundant of these gases, followed by carbon dioxide, sulfur dioxide, and smaller amounts of other compounds. Over hundreds of millions of years, countless eruptions released vast quantities of these gases, building up the atmosphere, layer by layer. The water vapor condensed into clouds, which rained down to form the oceans. The carbon dioxide contributed to the greenhouse effect, which kept the young Earth warm enough for liquid water to exist on the surface. Without volcanoes, Earth might have remained a dry, airless rock, unable to support life. Instead, volcanic activity provided the raw materials for an atmosphere and oceans, creating the conditions that made life possible. And even today, volcanoes continue to contribute to the atmosphere, though on a much smaller scale relative to the size of the atmosphere now. They're part of the carbon cycle, part of the water cycle, part of the complex web of processes that regulate the planet's climate and chemistry. It's worth pausing here to appreciate just how interconnected everything is. The heat in the Earth's core, generated by radioactive decay and ancient collisions, drives convection in the mantle. Convection moves tectonic plates. Plates collide and pull apart, creating volcanoes. Volcanoes release gases that build the atmosphere. The atmosphere supports life. Life alters the atmosphere further. And the whole system, vast and intricate, continues to evolve, driven ultimately by the energy deep inside the planet. You are part of this system. The oxygen you're breathing right now has cycled through this process countless times. The water in your body has been vapor in the sky, liquid in the ocean, ice in a glacier, and yes, steam in a volcanic plume. The calcium in your bones, the iron in your blood, these elements were forged in stars, scattered through space, gathered into the disk of dust that became our solar system, and incorporated into the Earth. Some of those atoms have passed through the mantle, melted into magma, erupted from a volcano, weathered into soil, and been taken up by plants that you or your ancestors ate. We are made of the Earth, and the Earth is made of stardust and time and heat. Let's think about heat flow for a moment, because it's central to understanding why volcanoes exist and why they're located where they are. Heat flows from hot regions to cold regions. This is a basic principle of thermodynamics. The Earth's interior is hot, and the surface, exposed to the cold of space, is relatively cool. So heat flows outward from the core toward the crust, and eventually into the atmosphere and out into space. But this flow isn't uniform. Some parts of the crust are thinner, allowing heat to escape more easily. Some parts of the mantle have rising plumes of hot rock, concentrating heat in specific areas. And some parts of the crust are being pulled apart by tectonic forces, creating gaps where magma can rise more easily. These variations in heat flow create the patterns we see in volcanic activity. Volcanoes aren't randomly distributed across the planet. They cluster in specific zones, primarily along tectonic plate boundaries and above mantle plumes. The Ring of Fire, for instance, is a horseshoe-shaped zone around the Pacific Ocean where a large number of earthquakes and volcanic eruptions occur. This zone exists because the Pacific Plate and several smaller plates are colliding with and sliding beneath the surrounding continental plates. When an oceanic plate is forced down into the mantle in a process called subduction, it carries water and other materials with it. As the plate descends, it heats up, and the water it carries lowers the melting point of the surrounding rock. This creates magma, which rises and feeds the volcanoes that line the edges of the Pacific. This is why the west coast of the Americas, the Aleutian Islands, Japan, the Philippines, and New Zealand all have active volcanoes. They're all part of the Ring of Fire, all sitting above subduction zones where oceanic crust is sinking into the mantle. But not all volcanoes are at plate boundaries. Some, like the Hawaiian Islands, form over hot spots, which are thought to be the surface expression of deep mantle plumes. These plumes are columns of hot rock rising from near the core mantle boundary, punching through the overlying mantle and crust like a blowtorch held against a sheet of metal. The plume stays relatively stationary while the tectonic plate above it moves, so the hot spot creates a chain of volcanoes over time, each one forming, becoming extinct as the plate carries it away from the plume, and being replaced by a new volcano that forms over the hot spot. The Hawaiian Islands are a perfect example of this. The big island, Hawaii, is currently over the hot spot and has active volcanoes. To the northwest, the older islands, Maui, Oahu, Kauai, are progressively older and have no active volcanoes because they've moved away from the hot spot. And beyond Kauai, stretching northwest across the Pacific, is a chain of underwater mountains called the Emperor Seamounts, all extinct volcanoes that were once over the Hawaiian hot spot millions of years ago. This chain is a timeline, a record of the Pacific Plate's movement, written in volcanic rock. Hot spots exist in other places too. Yellowstone is over a hot spot. Iceland sits on a hot spot that coincides with the Mid-Atlantic Ridge, which is why Iceland is both volcanically active and growing as the Atlantic spreads. Reunion Island in the Indian Ocean, the Galapagos Islands, the Canary Islands, all of these are hotspot volcanoes, each one a window into the deep mantle, a place where the Earth's inner heat finds a path to the surface. And then there are the rift zones, places where tectonic plates are pulling apart. The East African Rift is one of the most dramatic examples. Here, the African continent is slowly splitting in two. The rift is marked by a series of valleys, lakes, and volcanoes, all created by the stretching and thinning of the crust. As the crust thins, the pressure on the underlying mantle decreases, and the rock begins to melt. Magma rises, feeding the volcanoes at the rift valley. In a few million years, if the rifting continues, the eastern part of Africa may separate completely, and a new ocean will form between the two pieces. This is how the Atlantic Ocean began, as a rift between the Americas and Europe and Africa. And it's how the Red Sea formed, as Arabia split from Africa. The process is slow, but it's inexorable, driven by the heat and convection in the mantle below. So volcanoes are markers, signs of the Earth's inner workings, indicators of where heat is escaping, where plates are moving, where the planet is reshaping itself. And understanding this, understanding that volcanoes are part of a global system, makes them less frightening and more fascinating. They're not random disasters. They're predictable consequences of the way our planet works, expressions of forces that have been shaping the Earth since it formed. The movement of magma beneath the surface follows patterns older than mountains. When rock deep in the mantle grows warm enough, it becomes less dense and begins to rise. This rising is not sudden. It happens across thousands of years, a slow drift upward through layers of stone that themselves are moving, shifting, responding to heat and pressure in ways that seem almost fluid when stretched across geological time. As this warmer material ascends, cooler material sinks to take its place. The cycle continues, a vast circulation that operates on timescales beyond human perception. These convection currents in the mantle are what drive the motion of tectonic plates above. The continents themselves are passengers on this slow river of stone, moving at roughly the same speed your fingernails grow, a few centimeters each year, patient and inexorable. Magma forms when rock melts, and rock melts under specific conditions. Sometimes it is the addition of water that lowers the melting point, allowing solid stone to transition into liquid even when temperatures haven't changed dramatically. Water carried down into subduction zones, where one plate slides beneath another, seeps into the mantle, and encourages melting. This is how many of the world's volcanic arcs form, chains of volcanoes that follow the curves of colliding plates. Other times, Magma forms simply because pressure decreases. When mantle rock rises toward the surface, the weight pressing down on it lessens. With less pressure, the melting point drops, and what was solid becomes liquid. This happens at mid-ocean ridges, those long underwater mountain ranges where plates pull apart and new ocean floor is born. The magma wells up into the gap, cools, and becomes new crust, adding to the edges of the separating plates. There are also hot spots, places where plumes of especially warm mantle material rise from deep below, perhaps from near the boundary between mantle and core. These plumes are stationary, or nearly so, while the plates above them move. As a plate drifts over a hot spot, volcanoes form, then go extinct as they move away, and new volcanoes form in their place. The Hawaiian Islands are a classic example, a chain of volcanic islands that trace the movement of the Pacific Plate over millions of years. The composition of magma varies depending on where and how it forms. Magma that comes from the mantle tends to be rich in iron and magnesium, dark and relatively fluid when it erupts. This is basaltic magma, the kind that builds the ocean floor and creates the gentle shield volcanoes of Hawaii. It flows easily, spreading out in broad rivers of molten rock that can travel for miles before cooling. When magma rises through continental crust, it often melts some of that crust as well, mixing with it, becoming more silica-rich and viscous. This thicker magma doesn't flow as easily. It traps gases, builds pressure, and can lead to more explosive eruptions. But even these eruptions are part of a cycle, a process of recycling and renewing the planet's surface materials. Volcanic gases are mostly water vapor, along with carbon dioxide, sulfur dioxide, and other compounds. These gases were once dissolved in the magma, held in solution by the immense pressure underground. As magma rises and pressure drops, the gases come out of solution like bubbles forming in a bottle of soda when you open the cap. The expansion of these gases is what propels volcanic eruptions, driving magma upward and out. Water vapor released by volcanoes over billions of years is thought to be a major source of Earth's oceans. In the planet's early history, volcanic outgassing contributed vast amounts of water and other volatiles to the atmosphere. Over time, as the planet cooled, that water vapor condensed and fell as rain, filling the ocean basins. The air you breathe, the water you drink, much of it passed through a volcano at some point in deep time. Carbon dioxide from volcanic eruptions also plays a role in regulating Earth's climate over long time scales. When atmospheric carbon dioxide levels rise, the planet warms. Warmer temperatures increase rainfall and weathering of rocks, which draws carbon dioxide out of the atmosphere and locks it away in minerals. Volcanoes release carbon dioxide back into the cycle, maintaining a balance that has kept Earth habitable for billions of years. It is a thermostat of stone and gas, operating slowly, steadily, across eons. Magma chambers are not vast hollow caves filled with liquid rock, as they are sometimes imagined. Instead, they are regions of partially molten rock, a mixture of liquid, crystals, and solid rock, more like a sponge soaked with magma than an underground lake. The magma exists in pockets and networks within the rock, and only when enough of it accumulates and the pressure builds sufficiently does it force its way upward. The formation of a magma chamber can take tens of thousands of years. Magma arrives in pulses, small injections of molten material that gradually heat the surrounding rock, cause it to partially melt and expand the zone of melt. Crystals form and settle, changing the composition of the remaining liquid. The chamber evolves, matures, and eventually, if conditions are right, some of that magma finds a path to the surface. Not all magma reaches the surface. Much of it cools and solidifies underground, forming intrusive igneous rocks like granite. These rocks may eventually be exposed by erosion, revealing the frozen, plumbing systems of ancient volcanoes. The granite domes and cliffs you might see in mountain ranges were once magma chambers, now laid bare by millions of years of weathering. When magma does erupt, the style of eruption depends on its viscosity and gas content. Runny basaltic magma allows gases to escape easily, so eruptions tend to be effusive, with lava flowing out rather than exploding. Thicker, silica-rich magma traps gases, and when the pressure becomes too great, the magma shatters into fragments, creating explosive eruptions that send ash and rock high into the atmosphere. Even explosive eruptions, though, are not instantaneous. They can last for hours, days, or even months. The eruption column, that towering plume of ash and gas, rises because it is hot and buoyant. As it climbs, it entrains air, cools, and eventually reaches a height where it is no longer buoyant. There it spreads out, forming an umbrella-shaped cloud that can drift for hundreds of miles, depositing ash in layers that become part of the geological record. Volcanic ash is not like the ash from a wood fire. It is made of tiny fragments of rock and glass, sharp-edged and abrasive. When it falls, it blankets the landscape, smothering plants and collapsing roofs under its weight. But over time, volcanic ash weathers into fertile soil. The minerals it contains, especially phosphorus and potassium, nourish plants. Some of the most productive agricultural regions on Earth are built on volcanic soils. Lava flows, despite their dramatic appearance, are rarely dangerous to people. They move slowly enough, usually, that you can walk away from them. The real hazard is to structures and infrastructure. Lava doesn't care about property lines. It flows downhill, following valleys, consuming everything in its path, then cools into solid rock. The new rock becomes part of the landscape, a layer in the ongoing construction of the Earth's surface. There are different types of lava flows, each with its own texture and behavior. Pahoehoe is smooth and ropey, forming when fluid lava flows steadily and its surface cools into a flexible skin that wrinkles as the lava beneath continues to move. A is rough and jagged, a slower, thicker flow that breaks apart as it advances, creating a jumble of sharp, clinkery blocks. The names come from Hawaiian, where these types of lava are common and well observed. Lava tubes form when the surface of a lava flow cools and hardens while the interior remains molten and continues to flow. Eventually, the lava drains out, leaving behind a tunnel. These tubes can be vast, stretching for miles underground. Some are large enough to walk through, and they provide natural shelters and passageways. On the Moon and Mars, similar lava tubes have been identified, and they are considered potential sites for future human habitats, offering protection from radiation and temperature extremes. Pillow lava forms when lava erupts underwater. The outer surface chills instantly in contact with cold water, forming a glassy rind, while the interior remains molten and pushes forward, creating rounded, pillow-shaped masses. These pillows stack and pile up, building underwater volcanic structures. When you find pillow lava on land, it tells you that the rock formed beneath the sea, a clue to ancient ocean floors now uplifted into mountains. Volcanic islands are born from the sea, built layer by repeated eruptions. Each lava flow adds a little more height, a little more width. Over time, the island grows large enough to break the surface. At first, it is just a barren rock, swept by waves and wind. But eventually, seeds arrive, carried by birds or ocean currents. Plants take root in cracks, and soil begins to form. Life colonizes the new land, and the island becomes a green oasis in the ocean. The process of island formation is patient. It can take hundreds of thousands of years for a volcanic island to grow from the seafloor to the surface. And once it emerges, it continues to grow as long as the volcano remains active. The big island of Hawaii is still growing, still adding new land with each eruption of Kilauea and Mauna Loa. Mauna Loa is the largest volcano on Earth by volume. Measured from its base on the ocean floor to its summit, it is taller than Mount Everest. But because much of it is underwater, and because its slopes are gentle, it doesn't have the dramatic profile of a steep stratovolcano. It is a shield volcano, broad and low, built by countless flows of fluid basaltic lava. Shield volcanoes grow slowly, steadily, with eruptions that are relatively predictable and non-explosive. They are the gentle giants of the volcanic world. Their eruptions can still be hazardous, especially to property, but they rarely produce the catastrophic explosions associated with stratovolcanoes. The lava simply flows, and the mountain grows. Stratovolcanoes, by contrast, are steep-sided and built from alternating layers of lava and ash. They tend to erupt more explosively because their magma is thicker and traps more gas. These are the classic cone-shaped peaks that dominate many landscapes. Mountains like Mount Fuji, Mount Rainier, and Mount St. Helens. They are beautiful and dangerous, symbols of both creation and destruction. The eruption of Mount St. Helens in 1980 was a reminder of the power locked inside these mountains. The north face of the volcano collapsed in a massive landslide, releasing the pressure that had been building inside. The result was a lateral blast that flattened forests for miles and sent an ash cloud high into the stratosphere. But in the decades since, life has returned to the blast zone. Plants have recolonized the barren slopes, animals have moved back in, and the landscape is healing. Volcanic eruptions can influence climate, especially large ones that inject significant amounts of sulfur dioxide into the stratosphere. The sulfur dioxide reacts with water vapor to form tiny droplets of sulfuric acid, which reflects sunlight back into space. This can cool the planet temporarily, sometimes for a year or two. The eruption of Mount Pinatubo in 1991 cooled global temperatures by about 0.5 degrees Celsius for a couple of years. But even these climate effects are temporary. The droplets eventually fall out of the atmosphere, and temperatures return to normal. Volcanic eruptions are not a solution to human-caused climate change, but they do demonstrate the interconnectedness of Earth systems, the way events in one part of the planet can ripple outward and affect the whole. Volcanic lightning is one of the most striking phenomena associated with eruptions. It occurs when ash particles in the eruption column collide, generating static electricity. The result is spectacular bolts of lightning that flash through the ash cloud, illuminating it from within. It is a reminder that even in the midst of an eruption, the fundamental forces of physics are at work, the same forces that create thunderstorms and power the natural world. Geothermal energy is a gift from the Earth's interior, a way to tap into the planet's heat for human use. In areas with active or recent volcanism, heat is close to the surface. Water seeps down through cracks, is heated by hot rock, and rises back up, sometimes as hot springs, sometimes as steam. Geothermal power plants capture this steam and use it to drive turbines, generating electricity without burning fossil fuels. Iceland is a leader in geothermal energy, thanks to its position on the Mid-Atlantic Ridge, where the North American and Eurasian plates are pulling apart. The island is geologically young and volcanically active, with abundant geothermal resources. Most of Iceland's homes are heated with geothermal water, and a significant portion of its electricity comes from geothermal power. It is a model of how volcanic activity, often seen as a hazard, can also be a resource. Hot springs and geysers are surface expressions of geothermal systems. Hot springs are simply places where heated groundwater reaches the surface and pools. The water can be warm or scalding, depending on how deep it circulated and how much it cooled on the way up. Many hot springs are rich in dissolved minerals, which precipitate out as the water cools, forming colorful deposits of travertine or silica. Geysers are rarer and more dramatic. They occur when water is heated under pressure in an underground chamber, becomes superheated, and then suddenly flashes to steam, erupting in a fountain of boiling water and vapor. The cycle repeats as the chamber refills and heats again. Old Faithful in Yellowstone is perhaps the most famous geyser, erupting roughly every 90 minutes with remarkable regularity. Yellowstone itself sits atop a massive volcanic system, a supervolcano with a magma chamber that spans thousands of square kilometers. It has erupted explosively in the past, and it will likely erupt again someday, though no one knows when. The intervals between eruptions are hundreds of thousands of years, and there is no sign that an eruption is imminent. For now, Yellowstone is a wonderland of geothermal features, a window into the heat and power beneath our feet. The colors in Yellowstone's hot springs come from thermophilic bacteria and archaea, microorganisms that thrive in extreme heat. Different species prefer different temperatures, so the colors form concentric rings around the springs, with the hottest water in the center often too hot even for these hardy organisms. The brilliant blues, greens, yellows, and oranges are living communities, ecosystems adapted to conditions that would kill most other life. These thermophiles are more than just curiosities. They have taught scientists about the limits of life, expanding our understanding of where and how life can exist. Some of the enzymes discovered in thermophiles are now used in biotechnology, including the enzyme that makes PCR, a fundamental tool in genetics and medicine, possible. Life in volcanic hot springs has practical applications that reach far beyond the springs themselves. Hydrothermal vents on the ocean floor are another environment where volcanic heat supports life. These vents occur along mid-ocean ridges, where seawater seeps into cracks in the newly formed crust, is heated by magma below, and then jets back out, laden with minerals. The water can be hot enough to melt lead, but it cools rapidly as it mixes with the surrounding seawater. Around these vents, entire ecosystems flourish in complete darkness, independent of sunlight. Instead of photosynthesis, the base of the food web is chemosynthesis, a process where bacteria use the chemical energy in hydrogen sulfide and other compounds from the vents to produce organic matter. These bacteria are consumed by other organisms, building a community that includes giant tube worms, clams, crabs, and fish, all thriving in an environment that seems utterly inhospitable. The discovery of hydrothermal vent ecosystems in the late 1970s revolutionized biology. It showed that life does not require sunlight, that it can exploit other energy sources, and it raised the possibility that life might exist in similar environments elsewhere in the solar system, such as beneath the ice of Jupiter's moon Europa or Saturn's moon Enceladus, where liquid water and geological activity might create similar conditions. Volcanic minerals have been prized throughout human history. Obsidian, volcanic glass formed when lava cools so quickly that crystals don't have time to form, was used by ancient peoples to make sharp tools and weapons. It could be knapped in a blade sharper than surgical steel. Pumice, another volcanic rock, is so full of gas bubbles that it floats on water. It has been used as an abrasive for thousands of years. Sulfur deposits around volcanic vents were once a major source of this element, important for making gunpowder and later for industrial chemicals. Miners would venture into active volcanic craters to collect sulfur, dangerous work in toxic environments. Today, most sulfur is obtained as a byproduct of refining fossil fuels, but volcanic sulfur deposits remain a reminder of how deeply human industry has been connected to geological processes. Volcanic soils, as mentioned, are exceptionally fertile. The minerals released by weathering volcanic rock provide nutrients that plants need. Regions like the slopes of Mount Etna in Sicily, the valleys of Central America, and the islands of Indonesia have been farmed for centuries, supporting dense populations despite the volcanic hazards. The people who live there understand the trade-off. The same forces that threaten destruction also provide abundance. The Pacific Ring of Fire is a vast zone of volcanic and seismic activity encircling the Pacific Ocean. It is home to about 75% of the world's active volcanoes and 90% of the world's earthquakes. This is because the Ring of Fire traces the boundaries of several tectonic plates, places where plates collide, slide past each other, or pull apart. The energy released at these boundaries manifests as earthquakes and eruptions, a constant reminder of the dynamic nature of our planet. Despite the name, the Ring of Fire is not a continuous ring, but a series of arcs and trenches, each with its own geological story. The Andes, the Cascades, the Aleutians, Japan, the Philippines, Indonesia, New Zealand, all are part of this network of plate boundaries. The diversity of volcanic activity within the Ring of Fire reflects the variety of tectonic settings, from subduction zones to rift zones to transform faults. Living near a volcano requires a certain acceptance of risk, but it also fosters a deep connection to the Earth. Communities near active volcanoes often have rich traditions of monitoring and interpreting volcanic signs. They know the sounds the mountain makes, the smells of volcanic gases, the subtle changes in hot springs and fumaroles. This knowledge, passed down through generations, complements modern scientific monitoring and can provide early warnings of unrest. Modern volcano monitoring uses a combination of seismology, ground deformation measurements, gas analysis, and thermal imaging. Seismometers detect the earthquakes caused by magma moving underground. GPS stations measure how the ground swells or subsides as magma accumulates or drains. Gas sensors sample the emissions from fumaroles and craters, looking for changes in composition that might signal rising magma. Satellites provide thermal images that can detect hotspots and track eruption clouds. All this data is analyzed to assess volcanic hazard and issue warnings when necessary. Volcano observatories around the world work continuously, watching the mountains, ready to alert authorities and populations if an eruption seems imminent. This vigilance saves lives. The successful evacuations before the eruptions of Mount Pinatubo in 1991 and Age of Geological in 2010 are examples of how effective monitoring and communication can mitigate disaster. Yet prediction remains imperfect. Volcanoes are complex systems, and not every sign of unrest leads to an eruption. Sometimes a volcano will show all the signs: earthquakes, ground swelling, increased gas emissions, and then calm down without erupting. Other times, an eruption occurs with little warning. Scientists continue to refine their methods, learning from each event, building better models, but there is always uncertainty. This uncertainty is part of the nature of volcanic systems. They are sensitive to conditions we cannot fully observe, influenced by factors deep underground that we can only infer. But this does not mean we are helpless. The more we learn, the better we understand the patterns, the more accurately we can assess risk. And even imperfect warnings are valuable, giving people time to prepare, to evacuate, to protect themselves. The relationship between humans and volcanoes is ancient. Some of the earliest human tools were made from volcanic rock. Some of the first permanent settlements were built on volcanic soils. Myths and religions have been shaped by volcanic eruptions, with gods and spirits invoked to explain the fire and fury of the mountains. Volcanoes have been seen as gateways to the underworld, as the forges of gods, as living beings with moods and desires. In Hawaiian tradition, the volcano goddess Pele is both creator and destroyer, embodying the dual nature of volcanic activity. She is honored and respected, and offerings are made to her. This relationship is not one of fear alone, but of reverence, an acknowledgement that the land itself is alive and powerful, that humans are guests in a landscape shaped by forces far greater than themselves. In many cultures, volcanic eruptions are seen as transformative events, moments when the world is remade. And in a geological sense, this is true. Eruptions destroy, but they also create. They obliterate landscapes, but they also build new land. They end ecosystems, but they also provide the conditions for new ones to begin. This cycle of destruction and creation is fundamental to the Earth's story. The minerals formed in volcanic environments are themselves a kind of archive. Crystals in volcanic rock record the conditions under which they formed: temperature, pressure, composition of the magma. By studying these crystals, geologists can reconstruct the history of a magma chamber, trace the path magma took from deep in the mantle to the surface, and understand the processes that led to an eruption. Zircon crystals are particularly valuable for this. They are incredibly durable, resistant to weathering and alteration, and they incorporate uranium into their structure when they form. Uranium decays to lead at a known rate. So by measuring the ratio of uranium to lead in a zircon, scientists can determine when a crystal formed. Some zircons are billions of years old, survivors from the early Earth, tiny time capsules that tell us about a planet we can never visit except through the stories locked in stone. Volcanic rocks also preserve magnetic information. When lava cools, magnetic minerals within it align with the Earth's magnetic field, locking in a record of the field's direction at that moment. By studying the magnetization of volcanic rocks of different ages, scientists discovered that the Earth's magnetic field reverses periodically, with north and south magnetic poles swapping places. These reversals happen irregularly, every few 100,000 years on average, and they are recorded in the layered volcanic rocks of the ocean floor. This discovery was crucial to the development of plate tectonics theory. The pattern of magnetic reversals in oceanic crust, symmetrical on either side of mid-ocean ridges, provided strong evidence that new crust was being formed at the ridges and spreading outward. It was one of the key pieces of evidence that convinced the scientific community that the continents move, that the Earth's surface is dynamic and ever-changing. The heat driving all this activity comes, as we have seen, from the Earth's formation and from radioactive decay. The isotopes responsible, uranium, thorium, potassium, are scattered throughout the mantle and crust. Their decay is slow, steady, and will continue for billions of years. This means the Earth will remain geologically active for a very long time, far longer than humans have existed, far longer than we're likely to exist. But eventually, the Earth will cool. The heat will dissipate into space, the mantle will solidify, and volcanic activity will cease. Plate tectonics will stop. The planet will become geologically dead, like Mars, which lost its internal heat billions of years ago and no longer has active volcanoes or moving plates. But that future is so distant that it is almost beyond imagining, billions of years away, a timescale on which even mountains are temporary. For now, the Earth is alive, vibrant, constantly reshaping itself. Volcanoes are part of that life, expressions of the planet's inner energy. They remind us that the ground beneath our feet is not static, that the world is always in motion, always changing. And in that change, there's a kind of comfort, a reassurance that the processes that have sustained the Earth for billions of years continue, patient and powerful, beneath the surface. The mantle beneath our feet moves in patterns so slow they exist beyond the reach of human perception. Yet these movements shape everything we know about the surface world. Convection cells within the mantle rise and fall over millions of years, carrying heat from the deep interior toward the crust in rhythms that predate all living memory. These currents are not chaotic or violent, but orderly and patient, following the laws of fluid dynamics at temperatures and pressures we can barely imagine. The rock itself flows like honey, deforming grain by grain, crystal by crystal, in a process so gradual that mountains rise and fall within its tempo. The asthenosphere, that layer of partially molten rock beneath the rigid lithosphere, acts as a cushion and a conveyor at once. It allows the tectonic plates above to glide across its surface, carried along by the convection currents below. This layer is not entirely liquid, but soft enough to deform over geological time, responding to the weight of continents and the pull of sinking slabs. The temperature here hovers around 1300 degrees Celsius, hot enough to weaken the bonds between minerals, allowing them to slide past one another in slow motion. This softness is what makes plate tectonics possible, what allows the Earth's surface to renew itself over and over again. Subduction zones are places where one tectonic plate slides beneath another, descending back into the mantle in a process that recycles the ocean floor. These zones are among the most geologically active places on Earth, where earthquakes rumble and volcanoes rise in long arcs parallel to the trenches. The descending plate carries water and sediments down with it, and as it sinks deeper, the increasing pressure and temperature release that water into the mantle above. This water lowers the melting point of the surrounding rock, allowing magma to form even though the temperature hasn't increased. The magma rises, eventually feeding the volcanoes that form volcanic arcs like the Andes, the Cascades, and the islands of Japan. The process of subduction is slow, measured in centimeters per year, yet it is responsible for some of the most dramatic features on Earth's surface. The Mariana Trench, the deepest part of the ocean, marks where the Pacific Plate descends beneath the smaller Mariana Plate. Here, the ocean floor plunges more than 11 kilometers below sea level, creating a chasm so deep that if Mount Everest were placed inside it, the peak would still be covered by more than 2 kilometers of water. The pressure at these depths is immense, more than 1,000 times the atmospheric pressure at sea level. Yet life persists even here, adapted to conditions that seem impossible. Volcanic arcs are the surface expression of subduction, chains of volcanoes that form parallel to the trench where the plate descends. These arcs are often curved, following the geometry of the spherical Earth and the angle at which the plate subducts. The volcanoes in these arcs tend to be explosive, producing thick, viscous lava and violent eruptions, because the magma that feeds them is enriched with water and other volatiles from the subducting plate. This makes them different from the gentler shield volcanoes of hotspots, which produce runnier lava and more effusive eruptions. The contrast between these two types of volcanism reflects the different processes that generate their magma. Island arcs are volcanic arcs that form in the ocean, creating chains of islands like the Aleutians, the Kuriles, and the Lesser Antilles. These islands are born from the sea, built layer by layer through repeated eruptions over millions of years. They start as underwater volcanoes, growing taller with each eruption until they breach the surface and become islands. Over time, erosion and weathering shape them, and life colonizes their slopes, transforming barren rock into ecosystems. The soil on these islands is often rich in minerals from the volcanic rock, supporting lush vegetation despite the isolation. The Pacific Ring of Fire is a vast horseshoe-shaped zone encircling the Pacific Ocean, home to about 75% of the world's active volcanoes. This ring is not a single feature, but a collection of subduction zones, each with its own characteristics and history. The ring includes the volcanic arcs of the Western Pacific, the Andes of South America, the Cascades of North America, and the volcanoes of Alaska and the Aleutian Islands. It is a testament to the dynamic nature of the Pacific Plate, which is being subducted beneath the surrounding plates in multiple locations. The Ring of Fire is also where about 90% of the world's earthquakes occur, a reminder that volcanism and seismicity are closely linked. Hot spots are another source of volcanic activity, distinct from plate boundaries. These are places where plumes of hot mantle material rise from deep within the Earth, possibly from the boundary between the mantle and the core. The plumes remain relatively stationary while the tectonic plates move over them, creating chains of volcanoes that record the direction and speed of plate motion. The Hawaiian Islands are the classic example of a hotspot chain, with the youngest and most active volcano, Kilauea, located over the hotspot, and progressively older islands stretching to the northwest. The oldest islands in the chain have eroded down to sea level and beyond, forming underwater seamounts that mark the ancient path of the Pacific Plate. The Hawaiian hotspot has been active for at least 70 million years, producing a chain of volcanoes that extends across the Pacific Ocean floor. The bend in the Hawaiian Emperor Seamount chain, which occurred about 47 million years ago, records a change in the direction of the Pacific Plate's movement. This bend is visible in the geometry of the seamounts, a fossilized record of plate tectonics written in volcanic rock. The hotspot continues to feed Kilauea and Mauna Loa today, and a new underwater volcano, Loihi, is growing on the seafloor to the southeast, destined to become the next Hawaiian island in tens of thousands of years. Mantle plumes are thought to originate from the core mantle boundary, nearly 3,000 kilometers below the surface. At this depth, the temperature difference between the molten iron core and the solid rock mantle drives convection, and occasionally, a buoyant plume of hot rock detaches and rises toward the surface. The journey takes millions of years, and by the time the plume reaches the base of the lithosphere, it has cooled somewhat, but remains hot enough to melt and produce magma. The exact mechanism of plume formation is still debated among geologists, but the evidence for their existence is strong, found in the geochemistry of hotspot lavas and the long-lived nature of hotspot volcanism. Large igneous provinces are vast outpourings of lava that occur when a mantle plume first reaches the surface. These events are rare, happening perhaps once every few tens of millions of years. But when they do occur, they can cover millions of square kilometers with lava in a relatively short geological time. The Deccan Traps in India, the Siberian Traps in Russia, and the Columbia River Basalt Group in the northwestern United States are examples of large igneous provinces. These eruptions are thought to have had significant impacts on Earth's climate and ecosystems, releasing enormous amounts of gases into the atmosphere and potentially contributing to mass extinction events. The Siberian Traps erupted around 250 million years ago, coinciding with the Permian-Triassic extinction, the most severe mass extinction in Earth's history. The eruptions released vast quantities of carbon dioxide, sulfur dioxide, and other gases, which altered the climate and acidified the oceans. The lava covered an area larger than Europe, and the eruptions continued for perhaps 1 million years. The connection between the Siberian Traps and the extinction event is still being studied, but the timing and scale of the eruptions suggest they played a significant role. This reminds us that while volcanic activity is generally slow and creative, it can also, on rare occasions, have catastrophic consequences. Flood basalts are the layers of lava that make up large igneous provinces, typically composed of basalt, a dark, fine-grained volcanic rock. These lavas are very fluid when erupted, allowing them to flow great distances and cover vast areas. Individual lava flows can be tens of meters thick and extend for hundreds of kilometers. The Columbia River Basalt Group, which erupted between 17 and 6 million years ago, consists of more than 300 individual lava flows, stacked one atop another. The landscape they created is characterized by flat-top plateaus and steep-walled canyons, where rivers have cut through the layers of basalt, exposing the stratigraphy. The gases released during volcanic eruptions have played a crucial role in shaping Earth's atmosphere and climate over geological time. Water vapor, carbon dioxide, sulfur dioxide, and other gases are released from magma as it rises and the pressure decreases. Over Earth's history, volcanic outgassing has contributed to the formation of the oceans and the atmosphere, providing the water and gases necessary for life. In the short term, large eruptions can inject sulfur dioxide into the stratosphere, where it forms aerosols that reflect sunlight and cool the planet for a few years. The eruption of Mount Pinatubo in 1991, for example, cooled global temperatures by about half a degree Celsius for several years. Volcanic aerosols are tiny particles and droplets suspended in the atmosphere, formed when volcanic gases react with water vapor and other atmospheric components. Sulfur dioxide from eruptions combines with water to form sulfuric acid droplets, which can remain in the stratosphere for years, scattering sunlight and creating vivid sunsets. These aerosols can also affect weather patterns and precipitation, though the effects are complex and vary depending on the location and size of the eruption. The study of volcanic aerosols helps scientists understand both past climate changes and the potential impacts of future eruptions. Volcanic winters are periods of cooling that can follow very large eruptions, when the amount of sunlight reaching Earth's surface is reduced by volcanic aerosols. The eruption of Mount Tambora in 1815, the largest eruption in recorded history, led to the year without a summer in 1816, when temperatures in the northern hemisphere dropped significantly, causing crop failures and food shortages. Snow fell in June in New England, and frost occurred throughout the summer in Europe. This event illustrates the power of volcanic eruptions to influence climate on a global scale, though such extreme eruptions are rare, occurring perhaps once every few centuries. The study of ice cores from Greenland and Antarctica provides a record of past volcanic eruptions, preserved as layers of volcanic ash and sulfate deposits. These cores allow scientists to reconstruct the history of volcanism over hundreds of thousands of years, identifying major eruptions and estimating their size and impact on climate. The ice also traps air bubbles, which preserve samples of the ancient atmosphere, allowing researchers to measure past levels of carbon dioxide, methane, and other gases. This long-term perspective helps us understand the natural variability of Earth's climate and the role of volcanic activity within it. Geothermal gradients describe how temperature increases with depth below Earth's surface. On average, the temperature rises by about 25 to 30 degrees Celsius per kilometer of depth, though this varies depending on location and geological setting. In areas with active volcanism or thinning crust, the geothermal gradient is steeper, and heat from the mantle is closer to the surface. This is what makes geothermal energy viable in places like Iceland, New Zealand, and parts of the western United States, where hot rock or magma is within a few kilometers of the surface. Geothermal reservoirs are underground pockets of hot water and steam, heated by magma or hot rock below. These reservoirs can be tapped for energy by drilling wells and bringing the steam or hot water to the surface, where it drives turbines to generate electricity. Geothermal energy is renewable because the heat source is continuously replenished by the Earth's internal heat, and it produces very little greenhouse gas emissions compared to fossil fuels. Countries with active volcanic regions, like Iceland, generate a significant portion of their electricity from geothermal sources, and the technology is expanding to other regions with suitable geology. Hot springs and geysers are surface expressions of geothermal activity, where heated groundwater emerges naturally. Hot springs occur when water percolates down through cracks in the rock, is heated by proximity to magma or hot rock, and then rises back to the surface. The water can be rich in dissolved minerals, which precipitate out as the water cools, forming colorful terraces and deposits. Geysers are a special type of hot spring where the plumbing system allows pressure to build until the water explosively erupts as steam and boiling water. Old Faithful in Yellowstone is perhaps the most famous geyser, erupting roughly every 90 minutes with remarkable regularity. The colors in hot springs come from thermophilic microorganisms, heat-loving bacteria, and archaea that thrive in water temperatures that would kill most other life forms. These microorganisms contain pigments that help them capture light or protect them from ultraviolet radiation, and the different species prefer different temperatures, creating bands of color around springs. The Grand Prismatic Spring in Yellowstone is a stunning example, with deep blue water in the center, where the temperature is too hot for most life, surrounded by rings of green, yellow, orange, and red, each color representing a different community of microorganisms. These extremophiles are of great interest to scientists studying the origins of life and the potential for life on other planets. Hydrothermal vents on the ocean floor are underwater hot springs, where seawater seeps into the crust, is heated by magma, and then erupts back into the ocean, often at temperatures exceeding 400 degrees Celsius. The water is rich in dissolved minerals and chemicals, which precipitate out when the hot water meets the cold ocean, forming chimney-like structures called black smokers or white smokers, depending on the minerals involved. These vents support unique ecosystems that do not rely on sunlight, but instead derive energy from the chemicals in the vent fluids, a process called chemosynthesis. Bacteria at the base of the food chain oxidize hydrogen sulfide and other chemicals, and they in turn support a community of tube worms, clams, crabs, and other organisms. The discovery of hydrothermal vent ecosystems in 1977 revolutionized our understanding of life's possibilities. Before this, it was assumed that all ecosystems ultimately depended on photosynthesis, but the vent community showed that life could thrive in complete darkness, powered by Earth's internal heat. This discovery has implications for the search for life elsewhere in the solar system, particularly on moons like Europa and Enceladus, which have subsurface oceans that might harbor similar hydrothermal systems. The resilience and adaptability of life in these extreme environments suggests that life might be more widespread in the universe than previously thought. Pillow lavas form when lava erupts underwater, cooling so rapidly that it forms rounded, pillow-shaped masses. The outer surface of each pillow cools and solidifies almost instantly upon contact with the cold water, while the interior remains molten for a time, allowing the pillow to inflate. As more lava erupts, new pillows form on top of the old ones, creating a pile of bulbous shapes. Pillow lavas are a common feature of mid-ocean ridges, where the seafloor is spreading and new crust is forming. They are also found in ancient rocks that were once part of the ocean floor, but have since been uplifted onto land, providing evidence of past tectonic settings. Ophiolites are sections of oceanic crust and upper mantle that have been thrust on a continental crust during tectonic collisions. These rock sequences are invaluable to geologists because they provide a cross-section through the oceanic lithosphere, which is otherwise hidden beneath kilometers of seawater. Ophiolites typically include pillow lavas at the top, underlain by sheeted dikes, gabbro, and finally peridotite from the mantle. Studying ophiolites allows scientists to understand the processes that occur at mid-ocean ridges and the structure of the oceanic crust, even though they can't easily access the seafloor directly. The rock cycle is the slow transformation of rocks from one type to another over geological time, driven by Earth's internal heat and surface processes. Igneous rocks form from the cooling of magma or lava. Sedimentary rocks form from the accumulation and cementation of sediments. And metamorphic rocks form when existing rocks are subjected to high heat and pressure, causing them to recrystallize without melting. Volcanic activity is a key part of the rock cycle, creating new igneous rocks and contributing to the formation of sediments through weathering and erosion. Over millions of years, rocks can be subducted, melted, and erupted again, completing the cycle. Metamorphism occurs when rocks are subjected to conditions of temperature and pressure that are different from those in which they formed, causing changes in their mineral composition and texture. This typically happens deep within the crust, where the heat from the mantle or from nearby magma bodies causes the minerals in the rock to recrystallize into new forms that are stable at the higher temperatures and pressures. Metamorphic rocks often have a layered or banded appearance, called foliation, which results from the alignment of minerals under directed pressure. Examples include slate, schist, and gneiss, each representing different degrees of metamorphism. Contact metamorphism occurs when magma intrudes into cooler surrounding rock, heating it and causing localized metamorphism. The zone of altered rock around the intrusion is called a contact aureole, and its width depends on the size of the intrusion and the temperature difference. Minerals in the contact aureole can include andalusite, cordierite, and garnet, which form at high temperatures. Contact metamorphism is often visible in the field as a change in color or texture of the rock near an igneous intrusion, and it provides evidence of past volcanic activity even when the volcano itself has long since eroded away. Regional metamorphism occurs over large areas, typically associated with mountain building and tectonic collisions. When continents collide, the crust is thickened and rocks are buried to great depths, where they experience high temperatures and pressures. Over millions of years, these rocks are metamorphosed, and eventually, they may be uplifted and exposed to the surface through erosion. The Appalachian Mountains, the Himalayas, and the Alps all contain extensive regions of metamorphic rock, recording the history of ancient collisions and the deep processes that occur during mountain building. Minerals are the building blocks of rocks, naturally occurring crystalline solids with specific chemical compositions and ordered atomic structures. Each mineral has characteristic physical properties, such as hardness, color, luster, and cleavage, which can be used to identify it. Volcanic rocks contain minerals like olivine, pyroxene, plagioclase feldspar, and quartz, depending on the composition of the magma for which they formed. The study of minerals, called mineralogy, helps geologists understand the conditions under which rocks formed and the processes that have affected them since. Crystals form when atoms arrange themselves in repeating patterns as a mineral solidifies. The size of the crystals depends on the rate of cooling. Slow cooling allows large crystals to grow, while rapid cooling produces small crystals or even glass, where the atoms don't have time to organize into a crystalline structure. Intrusive igneous rocks, which cool slowly underground, have large crystals and a coarse-grained texture, while extrusive igneous rocks, which cool quickly at the surface, have small crystals and a fine-grained texture. Obsidian, volcanic glass, forms when lava cools so rapidly that no crystals form at all, resulting in a smooth, glassy texture. Pumice is a volcanic rock so full of gas bubbles that it can float on water. It forms when gas-rich magma erupts explosively, and a sudden drop in pressure causes the dissolved gases to expand rapidly, creating a froth. The froth solidifies before the bubbles can escape, trapping them in the rock. Pumice is light, abrasive, and porous, and it has been used for centuries as a cleaning and polishing material. Large rafts of pumice can form after submarine eruptions, floating on the ocean surface and drifting with currents, sometimes traveling thousands of kilometers before sinking or washing ashore. Scoria is another type of vesicular volcanic rock, similar to pumice but denser and darker in color. It forms from basaltic magma, which is less dissolved gas than the rhyolitic magma that produces pumice. Scoria typically has larger, more irregular vesicles and does not float on water. It is commonly found around cinder cones, where blobs of molten lava are ejected into the air, cool, and solidify as they fall and accumulate around the vent. Scoria is often used as a decorative stone in landscaping and as aggregate in lightweight concrete. Volcanic bombs are large fragments of molten or semi-molten lava that are ejected during explosive eruptions. They cool and solidify as they fly through the air, and their shapes reflect their molten state. Some are rounded, others are elongated or twisted, and some have aerodynamic shapes with smooth surfaces. Volcanic bombs can be several meters across and weigh many tons, and they can travel hundreds of meters from the vent. Finding a volcanic bomb in the field is a reminder of the violence that can accompany some eruptions, though most volcanic activity is far gentler. Tephra is a general term for all the fragmented material ejected during a volcanic eruption, regardless of size or composition. It includes ash, lapilli, and volcanic bombs. Tephra layers are important in geology because they can be dated and correlated across wide areas, providing time markers in the rock record. A single large eruption can deposit a distinctive layer of ash over thousands of square kilometers, and this layer can be used to synchronize events in different locations. Tephra layers are particularly useful in archaeology, where they can help date human artifacts and settlements. Volcanic ash is not like the ash from a wood fire. It is made of tiny fragments of volcanic glass and minerals, sharp and abrasive. The particles are so small that they can remain suspended in the atmosphere for days or weeks, traveling thousands of kilometers from a source. Ash can damage aircraft engines, disrupt air travel, and pose health risks if inhaled. It also affects agriculture, smothering crops and contaminating water supplies. However, over the long term, volcanic ash weathers into fertile soil, enriching the land with nutrients. Many of the world's most productive agricultural regions, such as the slopes of Mount Etna and the volcanic soils of Java, owe their fertility to ancient ash deposits. Lahars are volcanic mudflows, mixtures of water and volcanic debris that flow down the slopes of volcanoes, often following river valleys. They can be triggered by heavy rainfall, the melting of snow and ice during an eruption, or the collapse of Crater Lake. Lahars can travel at speeds of tens of kilometers per hour and can be highly destructive, burying everything in their path. The 1985 eruption of Nevado del Ruiz in Colombia generated lahars that traveled more than 100 kilometers and killed more than 20,000 people in the town of Armero. Monitoring and early warning systems are crucial in areas where lahars are a hazard. Crater lakes form in the calderas or craters of dormant or extinct volcanoes, where water accumulates from rainfall, snowmelt, or groundwater. These lakes can be stunningly beautiful, with deep blue or green water surrounded by steep volcanic walls. Some crater lakes are acidic, heated by volcanic gases rising from below, while others are cold and fresh. Crater Lake in Oregon, the deepest lake in the United States, formed about 7,700 years ago when Mount Mazama collapsed during a massive eruption, creating a caldera that later filled with water. The lake is renowned for its clarity and deep blue color, a result of its purity and depth. Volcanic islands are born from the sea, built by repeated eruptions that pile lava and ash above the ocean surface. The process can take hundreds of thousands of years, and once the island emerges, it becomes a blank slate for life to colonize. Seeds arrive on the wind or in the droppings of birds. Spores drift in on air currents, and insects and other small creatures hitch rides on floating debris. Over time, ecosystems develop, from pioneer species that can tolerate the harsh conditions to more complex communities as soil develops and conditions improve. The Hawaiian Islands are a classic example, each island representing a different stage in this process, from the young, active volcanoes of the Big Island to the older, heavily eroded islands to the northwest. Volcanic soils, called Andesols, are among the most fertile in the world, rich in minerals and nutrients released by the weathering of volcanic rock. These soils are typically dark, well-drained, and high in organic matter, making them ideal for agriculture. Regions with volcanic soils, such as Java, the slopes of Mount Etna, and parts of Central America, support dense human populations and intensive farming. The fertility of volcanic soils is one reason why people continue to live near active volcanoes despite the risks, a testament to the balance between danger and opportunity that volcanism represents. The weathering of volcanic rock releases elements like potassium, phosphorus, calcium, and magnesium, which are essential nutrients for plants. Basaltic rocks, common in volcanic regions, weather relatively quickly compared to other rock types, releasing these nutrients over timescales of decades to centuries. This rapid weathering is one reason why volcanic soils are so productive, but it also means that the nutrients can be depleted if the land is overused. Sustainable farming practices, including crop rotation and the addition of organic matter, help maintain the fertility of these soils over the long term. Carbon sequestration by weathering is a slow but important process in Earth's carbon cycle. When volcanic rocks weather, they react with carbon dioxide from the atmosphere, converting it into dissolved bicarbonate ions that are carried by rivers to the ocean, where they eventually precipitate as carbonate minerals and sediments. This process removes carbon dioxide from the atmosphere over millions of years, acting as a natural thermostat that helps regulate Earth's climate. Periods of increased volcanic activity and mountain building can enhance weathering rates, drawing down atmospheric carbon dioxide and potentially leading to global cooling. The long-term carbon cycle operates on timescales of millions of years, balancing the input of carbon dioxide from volcanic outgassing with the removal of carbon dioxide through weathering and the burial of organic matter. This cycle is fundamental to understanding Earth's climate history, including the ice ages and the warm periods in between. Human activities are currently adding carbon dioxide to the atmosphere much faster than natural processes can remove it, disrupting this balance and leading to climate change. Understanding the natural carbon cycle, including the role of volcanic activity, is essential for predicting future climate and developing strategies to mitigate the impacts of human emissions. Volcanic monitoring involves a variety of techniques to detect signs of unrest and predict eruptions. Seismometers measure earthquakes caused by the movement of magma. Gas sensors detect changes in volcanic gas emissions. GPS instruments track ground deformation as magma accumulates beneath the surface, and thermal cameras monitor changes in temperature. Satellite observations provide a broader view, detecting heat anomalies, ground deformation, and ash plumes. By integrating data from multiple sources, scientists can assess the likelihood of an eruption and provide warnings to authorities and the public. While predicting the exact timing and size of an eruption remains challenging, monitoring has greatly improved the ability to forecast volcanic activity and reduce risks. Volcano observatories are scientific institutions dedicated to monitoring and studying volcanoes. They operate networks of instruments, analyze data in real time, and issue warnings when necessary. The Hawaiian Volcano Observatory, established in 1912, is one of the oldest and has provided invaluable insights into the behavior of Kilauea and Mauna Loa. Other observatories around the world monitor volcanoes in places like Japan, Italy, Indonesia, and the Philippines, where large populations live near active volcanoes. These observatories are essential for public safety, providing the scientific basis for evacuation plans and hazard assessments. Volcanic hazard maps show the areas that could be affected by different types of volcanic activity, such as lava flows, pyroclastic flows, lahars, and ashfall. These maps are based on the volcano's past behavior, its geological setting, and computer models of how volcanic materials might spread. They are used by emergency managers to plan evacuations, by land use planners to guide development, and by the public to understand the risks they face. Hazard maps are not predictions of what will happen, but assessments of what could happen, providing a framework for preparedness and risk reduction. Living with volcanoes requires a balance of respect, preparedness, and adaptation. Communities near active volcanoes have developed strategies to cope with the risks, from building codes that account for ashfall and earthquakes to early warning systems and evacuation plans. In some places, Traditional knowledge and cultural practices play a role in risk reduction, as communities draw on generations of experience living with volcanic activity. Education is also crucial, helping people understand the hazards they face and the actions they can take to protect themselves. While the risks cannot be eliminated, they can be managed, allowing people to benefit from the fertile soils and geothermal energy that volcanoes provide. The journey through Earth's inner energy continues, moving now into the quieter rhythms of volcanic landscapes and the ways they transform over time. Volcanoes do not remain active forever. Most volcanic systems experience long periods of dormancy, stretching across thousands or even millions of years, during which the surface cools and life gradually reclaims the land. These sleeping volcanoes become part of the landscape in ways that feel permanent, their peaks softening under rain and wind, their slopes covered in forests or grasslands that show no obvious sign of the fire beneath. A dormant volcano is not extinct, it simply rests. The magma chamber below may still hold molten rock, but the pathways have closed or the pressure has eased. The volcano waits, and in that waiting, it becomes something else: a mountain, a valley, a lake. Communities build homes on its flanks. Rivers carve channels through its old lava flows. Birds nest in the crevices of its cooling rock. The volcano becomes woven into the fabric of daily life, no longer a source of fire, but a source of place. Some volcanoes do go fully extinct. These are systems where the magma source has moved away or exhausted itself, where the tectonic conditions that once fed the volcano have shifted. Extinct volcanoes erode slowly, their cones worn down by weather, their craters filled with sediment or water. Over millions of years, they may disappear entirely, their presence marked only by the types of rock left behind: basalt, andesite, rhyolite, stones that tell the story of ancient eruptions to anyone who knows how to read them. The transformation of a volcanic landscape is a study in patience. Lava flows, once molten and destructive, become fertile ground. The minerals within volcanic rock, potassium, phosphorus, calcium, iron, are released slowly as the rock weathers. Rain and wind break down the hard surface, creating soil that is rich and dark. This process takes decades, sometimes centuries, but the result is land that supports vigorous growth. Volcanic soils are among the most productive on Earth, which is why so many agricultural regions are found near volcanoes, both active and dormant. The Hawaiian Islands offer a clear example of this transformation. The Big Island, still actively growing through eruptions from Kilauea and Mauna Loa, has large areas of fresh lava rock, black, barren, and sharp. But as you move northwest through the island chain, the islands grow older. Oahu, Maui, Kauai. Each is progressively more eroded, more lush, more softened by time. Kauai, the oldest of the main islands, is covered in thick rainforest, its peaks carved into deep valleys by millions of years of rainfall. The volcanic origins are still visible, but they are draped in green, transformed by life. This progression from fire to forest is not unique to Hawaii. It happens wherever volcanoes fall silent and time moves forward. In Iceland, lava fields from eruptions centuries ago are now covered in moss, a thick carpet of green that softens the jagged rock. The moss grows slowly, just a few millimeters per year, but it is persistent. It traps moisture, breaks down the rock, and creates conditions for other plants to follow. Grasses take root, then shrubs, then eventually trees if the climate allows. The landscape heals itself, not by erasing the volcano, but by incorporating it. Volcanic craters often become lakes. When a volcano stops erupting, the crater at its summit may fill with rainwater, creating a body of water that is often strikingly blue or green due to the minerals dissolved in it. Crater Lake in Oregon is one of the most famous examples. Formed nearly 8,000 years ago after the collapse of Mount Mazama, the lake is the deepest in the United States. It's water fed entirely by rain and snowmelt. The water is extraordinarily clear because no rivers flow into it, carrying sediment. The lake sits in the caldera, calm and cold, a mirror reflecting the sky. Other crater lakes are found around the world. Lake Taupo in New Zealand fills a massive caldera created by one of the most powerful eruptions in recent geological history. Quilatoa in Ecuador is a smaller crater lake. Its waters a vivid turquoise due to dissolved minerals. These lakes become ecosystems of their own, supporting fish, birds, and plant life. They are places of quiet beauty, their volcanic origins hidden beneath the surface. Volcanic islands, once they stop growing, begin to sink. This is a slow process, driven by the cooling and contraction of the oceanic crust beneath them. As the island sinks, coral reefs may grow around its edges, building upward to stay near the sunlight. Over millions of years, the island can sink completely below the surface, leaving only the reef behind, a ring of coral encircling a lagoon. These are atolls, and they're the final stage in the life of a volcanic island. The volcano is gone, but its legacy remains in the shape of the reef. The Pacific Ocean is dotted with atolls, many of them in the Marshall Islands, the Maldives, and French Polynesia. Each atoll marks the location of a volcano that once rose above the waves, built by a hot spot, then carried away by the movement of the tectonic plate. The reef grew as the island sank, maintaining its position just below the water surface. The result is a landscape that seems impossibly delicate, a thin ribbon of coral and sand encircling a shallow lagoon, all of it resting on the submerged bones of an ancient volcano. The connection between volcanoes and coral reefs is one of the quieter partnerships in nature. The volcano provides the foundation, a stable, elevated platform in the middle of the ocean. The coral builds on that foundation, creating habitat for thousands of species. The reef protects the lagoon, and the lagoon becomes a nursery for fish and other marine life. The volcano, long extinct, continues to support life in a completely different form. Volcanic rock also plays a role in the carbon cycle, one of the planet's most important regulatory systems. When volcanic rock weathers, it reacts with carbon dioxide from the atmosphere. The CO2 dissolves in rainwater, forming a weak acid that breaks down the minerals in the rock. The carbon is then carried by rivers to the ocean, where it is used by marine organisms to build shells and skeletons. When these organisms die, their remains settle on the ocean floor, locking the carbon away in sediment. This process, called chemical weathering, removes carbon dioxide from the atmosphere over long timescales, helping to regulate Earth's climate. The rate of chemical weathering depends on several factors: temperature, rainfall, and the type of rock. Volcanic rock, especially basalt, weathers relatively quickly because it contains minerals that react readily with acidic water. This means that regions with extensive volcanic rock, such as Iceland or the Deccan Plateau in India, play a significant role in the global carbon cycle. The weathering of volcanic rock is one of the mechanisms that has kept Earth's climate relatively stable over millions of years, balancing the carbon released by volcanoes with the carbon removed by weathering. There is a rhythm to this process, a balance between the carbon released by volcanic eruptions and the carbon absorbed by weathering. Over short timescales, eruptions can release large amounts of CO2, warming the climate. But over long timescales, the weathering of the volcanic rock removes that carbon, cooling the climate. This balance is not perfect. There have been periods in Earth's history when volcanic activity was so intense that it overwhelmed the weathering process, leading to significant warming. But overall, the system has maintained conditions suitable for life. The Deccan Traps in India are a reminder of this dynamic. Formed by massive volcanic eruptions around 66 million years ago, The Deccan Traps released enormous quantities of lava and gas, covering an area larger than France. The eruptions likely contributed to climate changes that stressed ecosystems around the world. But over the millions of years since, the weathering of that volcanic rock has drawn down carbon dioxide, contributing to the cooling that followed. The Deccan Traps are still there, a vast plateau of basalt, slowly weathering under the monsoon rains. Volcanoes also create unique habitats that support specialized forms of life. Lava tubes, for example, are tunnels formed when the surface of a lava flow cools and hardens while molten lava continues to flow beneath. When the eruption ends, the lava drains away, leaving a hollow tube. These tubes can be hundreds of meters long, and they provide shelter from the extreme temperatures and UV radiation on the surface. In Hawaii, lava tubes are home to unique species of insects, spiders, and other invertebrates that have adapted to the dark, stable conditions inside. Some lava tubes contain ice, even in tropical climates. The tubes act as cold traps, where cool air sinks and remains, allowing ice to persist year-round. These ice caves are rare and fragile, their ice formations shaped by the slow drip of water and the circulation of air. They are places of stillness, where the temperature remains just below freezing even as the world outside warms and cools with the seasons. Fumaroles, the vents that release volcanic gases, also support specialized life. Around the edges of fumaroles, where the temperature is lower and moisture condenses, microorganisms thrive. These extremophiles can tolerate high temperatures, acidic conditions, and high concentrations of sulfur and other chemicals that would be toxic to most life. They are among the hardiest organisms on Earth, and they offer clues about how life might survive in extreme environments on other planets. The study of extremophiles has expanded our understanding of the limits of life. Researchers have found microorganisms living in boiling hot springs, in acidic lakes inside volcanic craters, and in deep-sea hydrothermal vents. These organisms use chemical energy rather than sunlight, breaking down sulfur compounds or methane to fuel their metabolism. They represent a form of life that does not depend on photosynthesis, suggesting that life could exist in places where sunlight never reaches, deep underground, or on other worlds. Volcanic landscapes also preserve traces of past climates and ecosystems. Ash layers and sediment cores provide a record of past eruptions, and the chemistry of the ash can reveal information about the composition of the magma and the conditions under which it erupted. Pollen and plant material trapped in ash layers offer snapshots of the vegetation that existed at the time of the eruption. These records help scientists reconstruct the history of a region, understanding how ecosystems have changed in response to volcanic activity and climate shifts. In some places, volcanic eruptions have preserved entire ecosystems in remarkable detail. The eruption of Mount Vesuvius in 79 CE buried the Roman cities of Pompeii and Herculaneum under meters of ash and pumice, preserving buildings, artifacts, and even the casts of people and animals. While tragic, this event created an unparalleled archaeological record, a frozen moment in time. Similarly, volcanic ash in other parts of the world has preserved fossils, footprints, and other traces of ancient life, providing windows into the past. The relationship between humans and volcanoes is complex. Volcanoes are hazards, capable of causing destruction and loss of life. But they are also sources of beauty, fertility, and energy. Many cultures have deep spiritual connections to volcanoes, viewing them as sacred places, homes of gods, or symbols of creation and destruction. In Japan, Mount Fuji is revered as a sacred mountain, a place of pilgrimage and artistic inspiration. In Hawaii, the volcano goddess Pele is honored and respected, her presence felt in every eruption. These cultural connections reflect and understanding that volcanoes are not simply geological features. They are part of the living landscape, dynamic and powerful. Living near a volcano requires a certain acceptance of risk, a recognition that the land is not entirely stable. But it also fosters a sense of place, a connection to the deep forces that shape the earth. Communities near volcanoes often have traditions and practices that reflect this relationship, from rituals to honor the volcano to practical knowledge about recognizing signs of unrest. Volcano monitoring has become increasingly sophisticated, allowing scientists to track changes in volcanic systems in real time. Seismometers detect earthquakes caused by moving magma. GPS stations measure ground deformation as magma pushes upward. Gas sensors analyze the composition and quantity of gases released from fumaroles and vents. Satellite instruments monitor heat emissions and changes in the shape of the volcano. All of this data is integrated to assess the likelihood of an eruption and to provide warnings to nearby communities. The goal of volcano monitoring is not to prevent eruptions. That is impossible, but to reduce risk by providing timely information. When a volcano shows signs of unrest, authorities can issue warnings, evacuate vulnerable areas, and prepare emergency services. This approach has saved countless lives. The eruption of Mount Pinatubo in the Philippines in 1991, for example, was preceded by weeks of increasing seismic activity and gas emissions. Scientists warned authorities, and tens of thousands of people were evacuated before the massive eruption. While the eruption caused significant damage, the death toll was far lower than it would have been without the warning. Not all eruptions can be predicted with such precision. Some volcanoes give little warning before erupting, and the science of forecasting eruptions is still developing. But the progress made in recent decades has been substantial, and it continues to improve as new technologies and methods are developed. The goal is to understand each volcano as an individual system, with its own behavior and patterns, rather than applying a one-size-fits-all approach. Volcanoes also offer opportunities for geothermal energy, a renewable resource that taps into the heat stored beneath the Earth's surface. In regions with active or recently active volcanoes, the heat is close to the surface, making it accessible for power generation. Geothermal power plants pump water into hot rock, where it is heated and turned to steam. The steam drives turbines, generating electricity. The water is then cooled and returned to the ground, creating a closed loop. Geothermal energy is reliable and consistent, unlike solar or wind power, which depend on weather conditions. A geothermal plant can operate continuously, providing a steady supply of electricity. Iceland generates nearly all of its electricity and heating from geothermal sources, taking advantage of its location on the Mid-Atlantic Ridge. New Zealand, the Philippines, Kenya, and other countries with volcanic activity also have significant geothermal capacity. The potential for geothermal energy extends beyond volcanic regions. Enhanced geothermal systems, which involve drilling deep into hot rock and creating artificial reservoirs, could make geothermal energy available in more places. This technology is still being developed, but it holds promise as a way to tap into the vast heat stored within the Earth, reducing reliance on fossil fuels. The heat from volcanoes also supports hot springs, which have been used by humans for thousands of years for bathing, healing, and relaxation. Hot springs form where groundwater is heated by volcanic rock or magma and rises to the surface. The water is often rich in dissolved minerals, which can have therapeutic properties. Hot springs are found in many volcanic regions, from Iceland to Japan to the western United States. In Japan, hot springs, or onsen, are an integral part of the culture. There are thousands of onsen throughout the country, ranging from rustic outdoor pools to elaborate resorts. The practice of bathing in hot springs is deeply relaxing, and the mineral-rich water is believed to have health benefits. The heat soothes muscles, the minerals nourish the skin, and the experience of sitting in warm water surrounded by nature is calming and restorative. Iceland also has a strong tradition of using geothermal water for bathing. The Blue Lagoon, one of the country's most famous attractions, is a geothermal spa fed by water from a nearby power plant. The water is a milky blue color due to silica and other minerals, and it remains warm year-round. Bathing in the Blue Lagoon, surrounded by black lava fields and steam rising into the cold air, is an experience that connects you to the volcanic forces beneath. Volcanic minerals have been valued throughout history for their beauty and utility. Obsidian, a volcanic glass formed when lava cools so quickly that crystals do not have time to form, was used by ancient peoples to make tools and weapons. Its edges can be sharper than steel, and it was highly prized for making cutting implements. Obsidian was also used for mirrors and decorative objects, its glossy black surface polished to a high shine. Pumice, the lightweight volcanic rock formed from frothy lava, has been used as an abrasive for cleaning and smoothing. It is still used today in cosmetics and industrial applications. Volcanic ash, rich in minerals, has been used as a soil amendment and in construction materials. The Romans used volcanic ash, or pozzolana, to make concrete that was remarkably durable. Roman concrete structures, such as the Pantheon and aqueducts, have lasted for 2,000 years, in part because of the volcanic ash in the mix. The study of volcanoes has also contributed to our understanding of other planets. Mars, Venus, and the moons of Jupiter and Saturn all show evidence of volcanic activity, past or present. Olympus Mons on Mars is the largest volcano in the solar system, a shield volcano that rises nearly 25 kilometers above the surrounding plains. It is no longer active, but its size and structure tell us about the volcanic processes that shaped Mars billions of years ago. Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions, driven not by internal heat from radioactive decay, but by tidal forces. Jupiter's immense gravity stretches and squeezes Io as it orbits, generating heat through friction. The result is a world covered in volcanoes, lava lakes, and plumes of sulfur that rise hundreds of kilometers into space. Io is a reminder that volcanic activity is not unique to Earth. It is a fundamental process that occurs wherever there is heat and pressure. Enceladus, a small moon of Saturn, also shows volcanic activity, though of a very different kind. Geysers near its south pole spray water ice and vapor into space, suggesting a subsurface ocean heated by tidal forces. This cryovolcanism, or ice volcanism, is driven by the same principles as volcanic activity on Earth. Heat from within causing material to erupt onto the surface. The discovery of these geysers has made Enceladus one of the most intriguing targets in the search for extraterrestrial life. Back on Earth, the study of ancient volcanic rocks has revealed patterns in the planet's history. Large igneous provinces, the remnants of massive volcanic events, are found on every continent. These provinces mark periods when the mantle was unusually active, producing enormous volumes of lava. Some of these events coincided with mass extinctions, suggesting that the volcanic activity had global consequences. But the rocks themselves also tell stories of resilience, of ecosystems that recovered and adapted. The Siberian traps, formed around 250 million years ago, are associated with the Permian-Triassic extinction, the most severe mass extinction in Earth's history. The eruptions released vast amounts of lava and gas, triggering climate changes that devastated life on land and in the oceans. But life did not end. In the aftermath, new species evolved, filling the niches left empty by the extinction. The Triassic period that followed saw the rise of the dinosaurs, a lineage that would dominate the planet for the next 150 million years. The Central Atlantic Magmatic Province, formed around 200 million years ago, marks another period of intense volcanic activity. This event coincided with the breakup of the supercontinent Pangaea as the Atlantic Ocean began to open. The eruptions were massive, but they also set the stage for the diversification of life in the Jurassic period. The opening of the ocean created new habitats, new opportunities, and new evolutionary pathways. These large igneous provinces remind us that Earth's history is punctuated by dramatic events, but also that the planet has a capacity for renewal. Volcanic activity, even when catastrophic, is part of the cycle that sustains life over the long term. The gases released by eruptions have built the atmosphere and oceans. The minerals released by weathering have enriched the soil. The heat from a mantle has driven the movement of continents, creating diverse environments and driving evolution. Volcanoes are also places of inspiration. Artists, writers, and filmmakers have been drawn to their power and beauty. Paintings of erupting volcanoes capture the drama of fire and ash against the sky. Poems and stories explore the symbolism of volcanoes as forces of creation and destruction, as metaphors for human emotion and experience. Films use volcanic eruptions as backdrops for adventure and disaster, tapping into our fascination with these powerful natural events. But beyond the drama, there is a quieter appreciation for volcanoes as part of the natural world. The gentle steaming of a fumarole, the warmth of a hot spring, the rich soil of a volcanic plain. These are the everyday expressions of Earth's inner energy. They are reminders that the planet is alive, that it changes and grows, and that we are part of that ongoing story. The minerals formed in volcanic systems are astonishingly diverse. As magma cools, different minerals crystallize at different temperatures, creating a sequence of formation. Olivine, a green mineral rich in magnesium and iron, forms early at high temperatures. Pyroxene and amphibole follow, then feldspar and quartz at lower temperatures. This process, called fractional crystallization, produces a range of rock types from a single magma source. The minerals can be identified by their color, hardness, and crystal structure, and they tell the story of the magma's journey from deep within the earth to the surface. Some volcanic minerals are gemstones. Peridot, the gem form of olivine, is found in basaltic lava and is prized for its bright green color. Garnets, which form in high-pressure environments, are sometimes found in volcanic rocks that have been brought up from the mantle. Opals, though not volcanic in origin, are sometimes found in volcanic ash deposits, where silica-rich water has percolated through the ash and precipitated the opal. These gemstones carry the beauty of the volcanic process, transformed into something precious. Volcanic landscapes also inspire scientific curiosity. Geologists study volcanoes to understand the processes that shape the earth. Biologists study the organisms that colonize new lava flows, exploring how life adapts to harsh conditions. Chemists analyze volcanic gases and minerals, uncovering the composition of the mantle and the reactions that occur at high temperatures. Physicists model the movement of magma and the dynamics of eruptions, using mathematics to describe the forces at work. Each discipline brings its own perspective, and together they create a comprehensive picture of how volcanoes function. This interdisciplinary approach is essential because volcanoes are complex systems, influenced by geology, chemistry, physics, and biology. Understanding them requires collaboration and the integration of diverse types of knowledge. Volcanoes also serve as natural laboratories for studying extreme conditions. The high temperatures, pressures, and chemical environments found in volcanic systems are difficult to replicate in a lab, but they occur naturally in volcanoes. By studying these conditions, scientists can learn about processes that are relevant to other fields, from material science to planetary science to the origins of life. The connection between volcanoes and the origins of life is particularly intriguing. Hydrothermal vents, both on land and under the sea, provide the chemical ingredients and energy sources that may have been necessary for the first living organisms. The minerals and gases released by these vents can drive chemical reactions that build complex organic molecules. Some scientists believe that life on Earth may have begun in such environments, where the conditions were just right for chemistry to become biology. This idea has implications for the search for life beyond Earth. If life can begin in the extreme conditions of a hydrothermal vent, then similar environments on other planets or moons might also support life. Enceladus, with its subsurface ocean and geysers, is one candidate. Europa, another moon of Jupiter, is thought to have a vast ocean beneath its icy crust, possibly warmed by tidal heating. These worlds may have hydrothermal systems similar to those on Earth, and they may harbor life. The exploration of these distant worlds is one of the great adventures of our time. Spacecraft have visited many of the planets and moons in our solar system, sending back images and data that reveal their volcanic histories. Future missions will search for signs of life, drilling into ice, sampling plumes, and analyzing the chemistry of alien oceans. The knowledge gained from studying Earth volcanoes will guide these explorations, helping us understand what to look for and how to interpret what we find. Back on Earth, the rhythm of volcanic activity continues, slow and patient. Magma rises, eruptions occur, landscapes are transformed, life adapts, ecosystems develop, and the planet renews itself. This cycle has been ongoing for billions of years, and it will continue for billions more. We are witnesses to a small part of this immense story, observers of processes that stretch far beyond our individual lives. There is comfort in this continuity, in knowing that the forces shaping the Earth are ancient and enduring. Volcanoes remind us that change is natural, that the planet is dynamic, and that stability is always temporary. But they also remind us that renewal is constant, that new land is always being created, and that life finds a way to flourish even in the harshest conditions. The story of Earth's inner energy continues even now, beneath you, beneath the oceans, beneath the mountains and plains. Every moment, heat flows upward from the core, spreading through the mantle in currents too slow to perceive, but powerful enough to move continents. This flow has never stopped since Earth's formation. It will continue for billions of years to come. The planet breathes in geological time, and volcanoes are part of that breath. When you think of a volcano, you might imagine a single mountain, a cone rising against the sky. But volcanoes are not isolated. They are connected to a vast system that spans the entire planet. The mid-ocean ridges form a continuous chain more than 60,000 kilometers long, wrapping around Earth like the seam on a baseball. Along this seam, magma rises constantly, creating new ocean floor, pushing the plates apart, renewing the surface. This process happens so slowly that you would never notice it in a lifetime. But over millions of years, it reshapes the world. The Atlantic Ocean grows wider each year, just a few centimeters, as the Mid-Atlantic Ridge continues its work. Iceland sits atop this ridge, a rare place where the undersea volcanic system rises above the waves. The island is split by the boundary between two tectonic plates, and you can walk through valleys where the Earth is literally pulling apart. Hot springs and geysers, the landscape, heated by magma chambers below. The island is young in geological terms, formed within the last 20 million years, and it continues to grow as new lava adds to its shores. Iceland's volcanoes have erupted many times in recorded history. Some eruptions have been gentle, with lava flowing steadily across fields and roads. Others have been explosive, sending ash into the atmosphere, disrupting air travel, reminding the modern world that Earth's processes continue regardless of human schedules. But even these dramatic events are part of a natural cycle. The ash settles, enriching the soil. The lava cools and becomes new rock. Mosses and lichens colonize the fresh surfaces within years. Grasses and shrubs follow. The land renews itself. The Icelandic people have learned to live with their volcanoes, not in fear, but in partnership. They harness geothermal energy for heating and electricity. They bathe in hot springs warmed by the earth. They farm on volcanic soil that yields abundant crops despite the northern latitude. Their language contains many words for different types of lava, different volcanic features, reflecting a deep familiarity with these processes. Volcanoes are woven into their culture, their stories, their daily lives. This relationship between people and volcanoes exists in many places. In Japan, Mount Fuji is revered as sacred, a symbol of beauty and endurance. Pilgrims climb its slopes, visiting shrines along the way. The mountain last erupted in 1707, but it remains active, monitored carefully, respected deeply. The volcanic soils around its base support agriculture. Hot springs in the region draw visitors seeking relaxation and healing. The mountain gives even as it holds the potential for future eruptions. In Italy, people have lived in the shadow of Vesuvius for thousands of years. The volcano destroyed Pompeii and Herculaneum in 79 CE, burying them in ash and preserving them for future generations to study. But the slopes of Vesuvius are also incredibly fertile, producing grapes for wine, vegetables, fruits. The volcanic soil is rich in minerals, and the Mediterranean climate is ideal for agriculture. Millions of people live in the Naples area, aware of the volcano, prepared with evacuation plans, but choosing to stay because this is their home, their history, their land. The balance between risk and reward defines many volcanic regions. The same processes that create danger also create opportunity. The geothermal heat that can fuel explosive eruptions also provides clean energy. The ash that can bury towns also enriches fields. The lava that destroys also builds new land. Understanding this balance helps us see volcanoes not as enemies, but as powerful natural forces that shape the world in complex ways. Volcanic eruptions have influenced human history in ways both obvious and subtle. Large eruptions can affect climate, cooling the planet temporarily by injecting sulfur dioxide into the stratosphere, where it forms reflective aerosols. The eruption of Mount Tambora in Indonesia in 1815 was the largest in recorded history. It ejected so much material into the atmosphere that the following year, 1816, became known as the year without a summer. Crops failed across Europe and North America. Snow fell in June in New England. Temperatures dropped worldwide. The disruption led to food shortages, migration, social unrest. Yet even this catastrophic event had unexpected consequences. The strange, vivid sunsets caused by volcanic aerosols inspired artists. The gloomy, cold summer of 1816 kept a group of writers indoors at a villa in Switzerland, where Mary Shelley conceived Frankenstein and Lord Byron wrote poetry reflecting the dark, apocalyptic mood. The eruption influenced culture as well as climate, demonstrating how deeply interconnected natural and human systems are. Smaller eruptions also leave their mark. The eruption of Laki in Iceland in 1783 released enormous amounts of sulfur dioxide, creating a toxic haze across Europe. The summer was hot, but the following winter was brutally cold. Crop failures and livestock deaths led to famine. Some historians believe this contributed to the social instability that fueled the French Revolution a few years later. Volcanoes can alter the course of history in ways that ripple far beyond their immediate surroundings. But volcanoes also enable history. The obsidian from volcanic regions provided sharp tools for ancient peoples. The fertile soil supported the rise of agriculture and civilization. The geothermal heat allowed early humans to settle in cold climates. Volcanic islands served as stepping stones for human migration across the Pacific. The story of humanity is intertwined with the story of volcanoes. On the island of Hawaii, the volcano Kilauea has been erupting almost continuously since 1983, with some pauses and changes in activity. For decades, visitors could watch lava flowing into the ocean, creating new land, sending up plumes of steam. The lava moved slowly enough that people could approach safely, observing the birth of new rock. The flows sometimes destroyed homes and roads, but they also added acres to the island. The Hawaiian people have a goddess, Pele, who embodies the volcano's creative and destructive power. She is honored, respected, understood as part of the natural order. The Hawaiian Islands themselves are a testament to volcanic creativity. Each island in the chain was formed by the same hot spot, a plume of magma rising from deep in the mantle. As the Pacific Plate moves northwest, it carries each volcano away from the hot spot. The volcano becomes extinct, begins to erode, and a new volcano forms over the hot spot. The Big Island of Hawaii is the youngest and most active. To the northwest, the islands grow progressively older, smaller, more eroded. Beyond the main islands, the chain continues as a series of seamounts and atolls, stretching thousands of kilometers, each one a former volcano, now worn down by time and waves. This process reveals something profound about Earth's surface. The plates are always moving, the hot spots are relatively stationary, and the result is a record written in stone, a timeline you can trace across the ocean floor. The Hawaiian Emperor Seamount chain extends all the way to the Aleutian Trench, where the oldest seamounts, formed more than 80 million years ago, are finally being subducted, returning to the mantle, completing the cycle. Other hotspots create similar chains. The Yellowstone hotspot has left a trail of volcanic calderas across the Snake River Plain in Idaho, marking the movement of the North American plate. The Réunion hotspot in the Indian Ocean created the Deccan Traps in India, then formed the Mascarene Islands, including Réunion itself, which remains volcanically active. These hotspots are windows into the deep mantle, places where plumes of hot rock rise from near the core mantle boundary, carrying heat and material upward through thousands of kilometers. The exact mechanism of hotspots is still debated among geologists. Some models suggest narrow plumes rising like columns. Others propose broader upwellings or multiple sources of heat. Seismic imaging has revealed some plume-like structures in the mantle, but the picture is not yet complete. This uncertainty is part of the beauty of science. We know enough to understand the basic processes, but there is still mystery, still room for discovery, still questions to explore. Volcanoes on Earth are part of a larger pattern of planetary volcanism. Throughout the solar system, worlds with internal heat experience volcanic activity, though the materials and mechanisms vary. On Io, Jupiter's moon, tidal heating from Jupiter's immense gravity creates intense volcanic activity. Io has hundreds of active volcanoes, erupting sulfur and silicate lava, constantly resurfacing the moon. It is the most volcanically active body in the solar system, a world where eruptions never cease. On Venus, volcanic features cover much of the surface. The planet has shield volcanoes, lava plains, and strange dome-like structures. Some scientists believe Venus may still be volcanically active, though confirming this is difficult due to the thick atmosphere and harsh surface conditions. The planet's volcanic history is written in its topography, in the patterns of lava flows visible through radar imaging. Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano more than 21 kilometers high and 600 kilometers wide. It is so large that if you stood on its summit, the base would be beyond the horizon. Olympus Mons is probably extinct now, but it was active for hundreds of millions of years, building up layer upon layer of lava. Mars also has the Tharsis region, a vast volcanic plateau, and the Elysium volcanic complex. These features suggest that Mars once had significant internal heat, driving volcanic activity that shaped the planet's surface. Even smaller bodies show signs of past or present volcanism. Enceladus, a moon of Saturn, has geysers erupting from its south pole, spraying water ice and organic molecules into space. These geysers are powered by tidal heating, similar to Io, but with water instead of rock. The plumes feed Saturn's E-ring, and they suggest that a subsurface ocean exists beneath Enceladus's icy crust, warmed by tidal friction and possibly by radioactive decay in the moon's core. Europa, a moon of Jupiter, likely has a similar subsurface ocean, kept liquid by tidal heating. The surface is covered in ice, crisscrossed with cracks and ridges, suggesting that the ice shell is constantly being reshaped by the movement of the ocean below. While Europa doesn't have volcanoes in the traditional sense, it may have cryovolcanism, where water or slushy ice erupts onto the surface instead of molten rock. This form of volcanism is driven by the same principle: internal heat seeking release. Triton, Neptune's largest moon, has geysers that erupt nitrogen gas, driven by sunlight warming nitrogen ice beneath the surface. This is a different mechanism than tidal heating, but it still represents a form of volcanic activity, a way for internal or subsurface material to reach the surface and reshape the landscape. These examples from across the solar system remind us that volcanism is a fundamental planetary process. Any world with sufficient internal heat will experience some form of volcanism, whether it involves molten rock, water, ice, or gases. The specifics depend on composition, size, distance from the sun, and tidal interactions, but the underlying principle remains the same. Heat must escape, and when it does, it transforms the surface. On Earth, the diversity of volcanic activity reflects the diversity of tectonic settings and magma compositions. We have already explored many types of volcanoes and eruptions, but there are always more details, more variations, more nuances to discover. Some volcanoes produce lava domes, thick, viscous mounds of lava that pile up around a vent rather than flowing away. These domes can grow for years, expanding slowly, sometimes collapsing, and sending pyroclastic flows down the slopes. Mount St. Helens, after its catastrophic eruption in 1980, spent years rebuilding a lava dome inside its crater. The dome grew intermittently, with periods of activity followed by quiet. Scientists monitored it closely, studying how domes form, how they collapse, how they signal changes in the volcano's behavior. The dome eventually grew hundreds of meters high before activity ceased. It sits now as a reminder of the volcano's power and its ongoing evolution. Some volcanoes erupt beneath ice, creating unique interactions between fire and ice. In Iceland, subglacial eruptions melt ice rapidly, creating floods called jökulhlaups. The meltwater mixes with ash and debris, forming a slurry that rushes down valleys, reshaping the landscape in hours. The eruption of Eyjafjallajökull in 2010 occurred partly beneath a glacier, and the interaction between magma and ice contributed to the explosive nature of the eruption and the production of fine ash that disrupted air travel across Europe. In Antarctica, Mount Erebus is the southernmost active volcano on Earth. It has a persistent lava lake in its summit crater, one of only a few in the world. The lava lake has been active for decades, glowing red in the polar darkness, a beacon of heat in the frozen continent. Erebus also produces unique volcanic bombs called volcanic crystals, large crystals of feldspar that form in the lava and are ejected during small explosions. These crystals can be found scattered around the summit, glittering in the ice. Submarine volcanoes, as we have discussed, form much of the ocean floor. but some rise high enough to create islands. The process of island formation is gradual. A seamount grows with each eruption, rising higher and higher until it finally breaks the surface. At first, it is just a rock, barren and wave-swept. But over time, life arrives. Seeds wash ashore or are carried by birds. Spores of ferns and mosses drift on the wind. Insects and other small creatures arrive, sometimes on floating debris. Slowly, the island becomes a living ecosystem. Surtsey, an island off the coast of Iceland, emerged from the ocean in 1963 during a volcanic eruption. Scientists have monitored it closely ever since, documenting the arrival of each new species, watching the ecosystem develop from nothing. Within years, plants were growing, birds began nesting, seals hauled out on the shores. The island became a natural laboratory for studying colonization and succession, showing how life takes hold even in the harshest, newest environments. This process has happened countless times throughout Earth's history. Every volcanic island was once barren rock. Everyone became, over time, a home for life. The Hawaiian Islands, the Galapagos, the Azores, the Canary Islands all began this way. Now, they host unique ecosystems, many with species found nowhere else on Earth, evolve in isolation, shaped by the particular conditions of their island homes. Volcanic islands often become biodiversity hotspots. The isolation encourages speciation, the development of new species adapted to local conditions. The Galapagos Islands, formed by a hotspot beneath the Nazca Plate, are famous for their unique wildlife, which inspired Charles Darwin's theory of evolution by natural selection. The islands are volcanically active, with eruptions occurring every few years, adding new lava to the landscape, creating new habitats, continuing the process of island building. The Galapagos finches, with their varied beak shapes adapted to different food sources, are a classic example of adaptive radiation. But the islands also host unique tortoises, iguanas, mockingbirds, and many other species. The marine environment is equally rich, with penguins, sea lions, marine iguanas, and diverse fish and invertebrates. All of this diversity stems ultimately from volcanic activity, which created the islands and continues to shape them. On a larger scale, volcanic activity has influenced the evolution of life on Earth. The formation of large, igneous provinces, which we discussed earlier, has been linked to mass extinctions, but also to periods of rapid evolutionary change. After each extinction, the survivors diversified, filling the ecological niches left empty. Volcanic activity, by altering the environment, drove evolution forward, creating new opportunities, new challenges, new forms of life. The Permian-Triassic extinction, the most severe in Earth's history, was followed by the rise of the dinosaurs. The Cretaceous-Paleogene extinction, caused partly by the Deccan Traps eruptions and the Chicxulub impact, cleared the way for mammals to diversify and eventually for humans to evolve. Volcanic activity is not just a backdrop to the story of life. It is an active participant, shaping the conditions in which life evolves. Volcanoes also create unique microclimates. The slopes of a large volcano can have dramatically different conditions at different elevations. At the base, tropical forests might thrive. Higher up, the climate becomes cooler, supporting different vegetation. Near the summit, conditions might be alpine or even barren. On a single mountain, you can pass through multiple climate zones, each with its own community of plants and animals. Mount Kilimanjaro in Tanzania is a famous example. It is a dormant volcano, rising nearly 6,000 meters above sea level. The base is surrounded by savanna and farmland. As you ascend, you pass through montane forests, then moorlands, then alpine desert, and finally the glaciers near the summit, though these are rapidly shrinking due to climate change. Each zone has distinct species, distinct conditions, all shaped by the volcano's height and the way it interacts with the atmosphere. Mountains, many of them volcanic, create rain shadows, influencing precipitation patterns. When moist air encounters a mountain, it rises, cools, and releases its moisture as rain or snow on the windward side. The leeward side, by contrast, is often dry, receiving little precipitation. This effect creates deserts and dry regions in the shadow of mountain ranges. The Andes create a rain shadow that contributes to the aridity of Patagonia. The Cascades create a rain shadow in eastern Washington and Oregon. Volcanoes, by building mountains, shape climate and ecosystems far beyond their immediate vicinity. The minerals formed in volcanic environments have practical uses beyond gemstones and construction materials. Zeolites, for example, are volcanic minerals with a porous structure that makes them useful as molecular sieves, catalysts, and absorbents. They're used in water purification, air separation, and industrial processes. Perlite, a volcanic glass that expands when heated, is used as a lightweight aggregate in construction and as a soil amendment in horticulture. Pumice, as mentioned earlier, is used in abrasives, polishes, and even in stone-washed denim. Volcanic ash, when fresh, can be a hazard to aviation, agriculture, and health. But once it settles and weathers, it becomes a resource. In some regions, volcanic ash is mined for use in cement production as a pozzolan, a material that reacts with lime to form compounds with cementitious properties. The Romans used volcanic ash from Pozzuoli, near Naples, to make concrete that has lasted for 2,000 years, including structures submerged in seawater. Modern engineers study Roman concrete to understand its durability, seeking to replicate its properties. The study of volcanoes, volcanology, combines fieldwork, laboratory analysis, and computer modeling. Volcanologists visit active volcanoes, collecting samples of lava, gas, and ash, measuring temperatures, recording seismic activity, observing eruptions from safe distances. They analyze samples to determine magma composition, crystal content, gas concentrations. They use seismometers, GPS stations, satellite imagery, and drones to monitor volcanic activity and detect signs of unrest. Computer models simulate magma movement, eruption dynamics, and the spread of ash and lava. These models help predict how an eruption might unfold, which areas might be affected, and how to mitigate risks. The models are constantly refined as new data becomes available, improving our ability to forecast volcanic behavior. Despite these advances, predicting volcanic eruptions remains challenging. Some volcanoes give clear warning signs: increased seismicity, ground deformation, changes in gas emissions. Others erupt with little warning. Each volcano is unique, with its own history, its own plumbing system, its own patterns. Volcanologists must consider all available data, understand the specific volcano they are monitoring, and communicate uncertainties honestly to authorities and the public. The relationship between science and society is crucial in volcanic regions. Scientists provide information, but decisions about evacuations, land use, and emergency response rest with governments and communities. Effective communication, trust, and preparedness are essential. In some cases, false alarms can erode trust, making future warnings less effective. In other cases, failure to heed warnings leads to tragedy. Balancing caution with the realities of people's lives is a constant challenge. The eruption of Nevado del Ruiz in Colombia in 1985 is a sobering example. The volcano showed signs of unrest for months, and scientists warned of the danger. But communication breakdowns, political hesitation, and lack of preparedness meant that warnings did not reach many people in time. When the eruption melted glaciers on the summit, lahars raced down the valleys, burying the town of Armero and killing more than 20,000 people. The tragedy led to improvements in volcano monitoring and disaster preparedness worldwide, but it remains a reminder of the human cost of volcanic hazards. In contrast, the eruption of Mount Pinatubo in the Philippines in 1991 was one of the largest of the 20th century, but relatively few people died because of effective monitoring, timely warnings, and successful evacuations. Scientists from the Philippine Institute of Volcanology and Seismology and the U.S. Geological Survey worked together, installing monitoring equipment, analyzing data, and issuing warnings as the volcano's unrest escalated. Tens of thousands of people were evacuated before the climactic eruption, saving countless lives. The eruption still caused significant damage. Ash and pyroclastic flows devastated the surrounding area. Lahars triggered by monsoon rains continued for years, burying towns and farmland. The eruption injected millions of tons of sulfur dioxide into the stratosphere, causing global temperatures to drop slightly for a couple of years. But the human toll was far less than it might have been, thanks to science, cooperation, and preparedness. These stories illustrate the dual nature of volcanoes: powerful, potentially dangerous, but also understandable, predictable to some degree, manageable with knowledge and preparation. Volcanoes are not malevolent. They are natural processes, expressions of Earth's internal energy, following physical laws. By studying them, we learn how to live alongside them, how to benefit from them, how to reduce risks. Geothermal energy, one of the most promising benefits of volcanic activity, is being developed in many countries. Iceland generates nearly all of its electricity and heating from geothermal and hydroelectric sources, making it one of the most sustainable energy systems in the world. New Zealand, Kenya, the Philippines, Italy, and the United States all have significant geothermal capacity. The technology is mature, reliable, and capable of providing baseload power, unlike solar and wind, which are intermittent. Enhanced geothermal systems, which involve drilling deep into hot rock and circulating water to extract heat, have the potential to expand geothermal energy beyond traditional volcanic regions. This technology is still being developed, but it could allow geothermal energy to be harnessed almost anywhere, tapping into the Earth's vast reservoir of heat. If successful, it could provide a significant portion of the world's energy needs, clean, renewable, and virtually inexhaustible. Volcanoes also offer opportunities for tourism and education. Volcanic landscapes are dramatic, beautiful, and fascinating. National parks like Yellowstone, Hawaii volcanoes, and Mount Rainier attract millions of visitors each year. People come to see geysers, lava flows, fumaroles, and volcanic peaks. They learn about geology, ecology, and the dynamic nature of the planet. This tourism supports local economies and fosters appreciation for natural processes. Volcanic regions often have cultural and spiritual significance. Many indigenous peoples view volcanoes as sacred, as dwelling places of gods or ancestors, as sources of life and power. These beliefs reflect a deep understanding of the volcano's role in the landscape, its provision of water, fertile soil, and resources. Respecting these cultural connections is important. Recognizing that scientific knowledge is one way of understanding volcanoes, but not the only way. In some cultures, offerings are made of volcanoes, rituals performed to honor them or seek their favor. These practices might seem superstitious from a scientific perspective, but they represent a relationship with the land, a recognition of forces larger than human control, a way of living in harmony with a powerful presence. Science and culture need not conflict. They can complement each other, each offering insights and meaning. The aesthetic beauty of volcanoes has inspired countless artists, writers, and photographers. The symmetry of a volcanic cone, the glow of lava at night, the drama of an eruption, the stark beauty of a lava field, all capture the imagination. Volcanoes appear in paintings, poems, films, and stories, symbolizing power, transformation, creation, and destruction. They are icons of nature's grandeur, reminders of forces beyond human scale. Photographers seek out volcanic eruptions, often at great personal risk, to capture images of lava fountains, ash plumes, and glowing flows. These images bring the reality of volcanoes to people who may never visit one, fostering awareness and wonder. They also document the events, providing a visual record that complements scientific data. Writers have used volcanoes as settings and metaphors. Jules Verne's Journey to the Center of the Earth begins with a descent into an Icelandic volcano. The story is fiction, but it reflects the fascination with what lies beneath the surface, the mystery of Earth's interior. Volcanoes represent gateways to the unknown, thresholds between the familiar surface and the hidden depths. In mythology, volcanoes are often associated with gods of fire and forge. Hephaestus in Greek mythology, Vulcan in Roman mythology, both were gods of metalworking and fire, said to have their workshops beneath volcanoes. The smoke and fire emerging from the mountain were evidence of their labor, forging weapons and tools for the gods. These myths personified the volcano, giving it agency and intention, a way of making sense of its behavior. The word volcano itself comes from Vulcan, the Roman god, whose forge was said to be beneath Mount Etna, or one of the volcanic islands near Sicily. The connection between fire, metalworking, and volcanoes reflects an understanding that intense heat can transform materials, that the Earth contains powerful forces capable of melting rock and reshaping the land. Modern science has replaced gods with physical processes, but the sense of awe remains. Understanding how volcanoes work does not diminish their power or beauty. It deepens our appreciation. We see not just a mountain, but a window into the planet's interior, a manifestation of heat and pressure, a process that has shaped the world for billions of years and will continue far into the future. As you lie here, perhaps you can imagine the slow currents of the mantle, the gradual rise of magma, the patient building of a volcanic cone. These processes happen on timescales far beyond human experience, yet they are always happening, always shaping the world. The ground beneath you is part of a tectonic plate, moving slowly, imperceptibly, carrying you along on a journey that spans millions of years. The heat you feel from the sun, the warmth of your bed, these are immediate and comforting. But there is another warmth, deep below, the warmth of Earth's interior, the heat that drives volcanoes and plate tectonics, the energy that has sustained geological activity for eons. This heat is always there, a steady presence, a reminder that the planet is alive in its own way, dynamic and ever-changing. Volcanoes are not separate from the rest of the Earth system. They are connected to the atmosphere through the gases they release, to the oceans through the water they heat and the islands they create, to the biosphere through the nutrients they provide and the habitats they form. They are part of the carbon cycle, the water cycle, the rock cycle. They influence climate, weather, and ecosystems. They are integral to the planet's functioning. Understanding this interconnectedness helps us see the Earth as a whole, a system where every part affects every other part. Volcanoes are not isolated phenomena. They are nodes in a network of processes that span the globe and reach deep into the interior. This perspective, the system's view, is essential for understanding how the planet works and how human activities interact with natural processes. Climate change, for example, is altering many aspects of the Earth system. Glaciers are melting, sea levels are rising, weather patterns are shifting. These changes can affect volcanoes in subtle ways. The melting of ice caps reduces the weight on the crust, which can influence magma movement and eruption rates in some volcanic regions. Rising sea levels can affect coastal and island volcanoes. Changes in precipitation can alter the frequency and intensity of lahars. Conversely, volcanic eruptions can influence climate, as we have discussed. Large eruptions inject sulfur dioxide into the stratosphere, cooling the planet temporarily. This effect is short-lived, lasting a few years at most, but it can be significant. After the eruption of Mount Pinatubo in 1991, global temperatures dropped by about half a degree Celsius for 2 years. This cooling was measurable and studied extensively, providing insights into how aerosols affect climate. Some scientists have proposed using artificial aerosols to cool the planet, a form of geoengineering intended to counteract global warming. This idea is controversial, with many potential risks and uncertainties, but it is inspired in part by observing the effects of volcanic eruptions, which provide natural experiments in how aerosols influence the climate system. Volcanoes, once again, teach us about the planet and about the consequences of altering the atmosphere. The study of past volcanic eruptions, preserved in ice cores, sediment layers, and tree rings, helps us understand the history of volcanic activity and its impacts. Ice cores from Greenland and Antarctica contain layers of volcanic ash and sulfate, marking major eruptions over hundreds of thousands of years. By analyzing these layers, scientists can date eruptions, estimate their size, and study their effects on climate and atmosphere. Tree rings also record volcanic eruptions. Large eruptions that cool the climate can cause trees to grow more slowly, producing narrower rings. By examining tree rings from ancient trees and preserved wood, scientists can identify years when growth was suppressed, often corresponding to known or suspected eruptions. This dendrochronology provides another line of evidence, cross-checking and refining the volcanic record. Sediment cores from lakes and ocean floors contain ash layers from past eruptions. These layers can be dated using various methods, providing a timeline of volcanic activity in a region. By correlating ash layers across different sites, scientists can reconstruct the history of individual volcanoes and understand patterns of activity over time. This work reveals that volcanic activity has varied over Earth's history. Some periods had more frequent or larger eruptions than others. Some regions were more active in the past than they are now. Understanding these patterns helps us assess current volcanic hazards and anticipate future activity. The volcanic record also intersects with human history. The eruption of Thera, a volcano in the Aegean Sea, around 1600 BCE, was one of the largest in human history. It destroyed the Minoan settlement on the island and may have contributed to the decline of the Minoan civilization. The eruption generated tsunamis that affected the surrounding coasts and ejected ash across a wide area. Some scholars have speculated that the eruption inspired the legend of Atlantis, though this remains debated. The eruption of Vesuvius in 79 CE, which buried Pompeii and Herculaneum, provides a detailed snapshot of Roman life, preserved under layers of ash and pumice. Archaeologists have excavated buildings, streets, artifacts, and even the casts of victims, providing insights into daily life, art, architecture, and society. The tragedy of the eruption created an unparalleled archaeological resource, a moment frozen in time. More recently, the eruption of Krakatoa in 1883 in Indonesia was heard thousands of kilometers away, generated tsunamis that killed tens of thousands, and produced vivid sunsets around the world for months. The eruption was documented by scientists, journalists, and witnesses, providing a wealth of information about the event and its effects. It also demonstrated the power of volcanic eruptions to affect the entire planet, not just the immediate vicinity. These historical eruptions remind us that volcanoes have always been part of human experience. They have shaped cultures, influenced events, and left lasting impressions. They are part of our shared story, woven into history, mythology, and memory. As you rest here, the story of volcanoes continues. Magma rises beneath the ocean floor, creating new crust. Hotspots build islands. Subduction zones generate explosive eruptions. Geothermal systems heat water and power turbines. Life thrives in volcanic soils and around hydrothermal vents. The processes are slow, patient, relentless. You are part of this story too. The atoms in your body were forged in stars and dispersed through space by supernova explosions. They came together on Earth, incorporated into rocks, released by weathering and volcanism, cycled through the biosphere. You are made of the same elements that form volcanoes, the same materials that flow as lava, that crystallize as minerals, that drift as ash. This connection is not poetic metaphor. It is literal truth. The calcium in your bones, the iron in your blood, the oxygen you breathe, all have passed through geological cycles, including volcanic processes. You are part of the Earth system, a temporary arrangement of atoms that will eventually return to the cycle, to be reused, transformed, renewed. Understanding this can be humbling and comforting. You are not separate from the planet. You are an expression of it, a moment in its long history. The same energy that drives volcanoes drives your metabolism. The same elements that form rocks form your body. The same cycles that shape the landscape shape your existence. Volcanoes, then, are not just geological features. They are reminders of connection, of continuity, of the deep processes that sustain the planet and everything on it. They are sources of creation, agents of change, expressions of energy that has flowed through the earth for billions of years. As the story draws toward a close, the volcanoes remain. They will erupt again, build new land, release gases, create habitats, shape climates. They will continue their slow work, indifferent to human timescales, following the rhythms of the Earth's interior. And we will continue to study them, live near them, benefit from them, and respect them. The most relaxing fact about volcanoes is perhaps this: they are part of a system that has worked for billions of years, a system that has created the conditions for life, that renews the surface, that cycles materials, that maintains balance. Volcanoes are not anomalies or threats, though they can be dangerous. They are essential, integral, natural. You can rest knowing that the Earth is doing what it has always done, what it will continue to do. The heat flows upward, the plates move, the magma rises. The processes are reliable, predictable in their broad patterns, even if individual events are uncertain. The planet is stable in its dynamism, constant in its change. And if you're still awake, still listening, there's more to explore. The story of Earth's inner energy extends in many directions, to the formation of the planet, to the origins of the atmosphere and oceans, to the deep biosphere, to the future of the planet as it continues to cool and evolve. Each thread leads to new discoveries, new wonders, new understandings. But for now, you can let the story settle. You can let the images of lava flows, volcanic islands, geothermal springs, and deep-sea vents fade into the background. You can let your mind rest, knowing that the Earth continues its work, that the processes are ongoing, that the cycle continues. The volcanoes will be there tomorrow and the day after, and for millions of years to come. They are patient, they are enduring, and they are, in their own way, a source of comfort, a reminder that the planet is alive, active, and capable of renewal. Rest now. Let the warmth of the Earth's inner energy be a gentle presence, a steady heat far below, supporting everything above. Let the story of volcanoes be a lullaby, a slow, rhythmic tale of creation and transformation, of fire and rock, of time and change. The Earth holds you. The processes continue, and you can rest.